So I've used the word shared windows often. WYSIWIS, anybody heard that term before?
What you see is what I see.
Very good. Excellent. Have you heard the term or you did? Excellent. So there's WYSIWYG and there's WYSIWIS. Okay. Shared windows. Okay, let's back off. A long time ago, we talked about the various functions that a collaborative application has to do. Okay, there has to be some session management. You saw that my library gives that to you. Okay, there has to be the single user interface. You guys implemented that. Okay, you decided you implemented the interactor, so you did that, and you did the model. Okay, and I hinted that you should do single user interface with a certain architecture. And then there was coupling, that my actions affected your output. Okay, and you saw a particular form of coupling in your application in the examples I gave you. And there's other things too, access control and concurrency control. And we're going to look at, they're very similar to each other because they're control functions. And in the assignment after shared windows, the assignment 3, we will do control, we will do locking. Okay, so right now I want to just focus on coupling and motivate shared window systems using coupling. Okay, and the coupling question really answers that given a certain input from a user, okay, what is the remote feedback? So the single user interface question answers given an input, what is the local feedback to that user? Okay, coupling answers what is the remote feedback. Okay, and the coupling we've seen so far, we saw what in class we saw an example. I gave you another example of this concert expense that multiple people are editing and displaying together. And I'm saying it is application specific. Do you guys agree? So the feedback that you see to my input depends. If I type "the woods are lovely, dark and deep," you get some feedback like this. And if I go and type number of attendees, you will go and hit return, you get to see the total expanded. So it seems application specific, right? And it depends on how I went and what is shared also is application specific. What is shared is the model we saw. What is the model? It's a very good question. We just say, oh, there is data and there is user interface and there's a very correct answer to that. But there isn't. And we guys who do research and collaboration, we say, well, the model could be, is the cursor caret position inside the model, where you are, or is it outside the model? And it's a tough question, and I kind of gave you the semantics. But in general, it's not easy to answer. And we guys who work in collaboration sometimes say, well, whatever is shared is the model. Whatever should be shared is the model. So it's a recursive definition. That in model sharing, we share the model. But what is the model? Well, what you really want to share. So of course, the model comes first and sharing comes later. But how to divide an application into model and view is not so easy. Okay, you can look at Word. Is the font part of the model, or is that part of the view? Right? And if you have seen various versions of Word, as they change Word, the fonts tend to remain. So the font is part of the model. But you might think that one user wants to go and see something in italics, another user wants to see something in bold. Why should that be part of the shared model? So it's tricky. And so coupling depends on the model interactive division. And we saw with sync that we can decide when changes are announced, when they're sent and when they're applied. So again, there's some variability. There's at least in the user's point of view, there is some variability. They don't quite know what to get. Okay, there's no well-defined answer. And in these systems, you can also determine, like in sync, you can determine whether this particular field is private or public. Okay, so just as you can have private and public files, you could imagine having private and public fields within a UI. Okay, so it's quite independent, application specific. So can we come up with an application independent definition of coupling? That's the question I'm going to raise here. Okay, and that's what I'm going to answer. So I'm going to focus not on the right coupling, but on what is application independent. And then maybe there's a spectrum of application independent couplings, and then we'll choose a right coupling among them. Okay? And what you guys did with your custom application is pretty much you decided what the coupling should be. But now when we're going to do things application independently, we're going to make some general decision, which means it may not be the right decision, but we somehow, for some reason, we want application independent coupling. And then we might get to range, and we'll choose the one that is the rightest, the most right. Okay? So why bother? Why bother with application independent coupling? We can divide our application into model and view, and we can then share the model, maybe using the automatic system. So, why bother? And in fact, historically, people came up with this kind of coupling first. Then they went to this custom coupling. So maybe, we are just going backwards. I've shown you the custom coupling, so, why bother with this application independent coupling?
Because an application independent coupling makes our models and our views more extensible than if every new property we want to add, we have to add all this boilerplate to support it the right way.
Okay, so the question has to do with implementation, and the answer has to do with implementation. That look, if we are going to have application-specific coupling, then as the application changes, we have to change the application. As the application changes, we have to go and change the coupling also, and as we change more properties, we have to do some extra work, and so so this is related to automation for sure. Okay. But like I said, we could have a sync-like system that shares the model automatically. So as you change properties, they get shared. Okay, that's exactly what happens in sync. It's really nice that way. Okay. But you did have to go and decide how to divide your application into model and interactive. In the first assignment, if I just told you, take my GUI, implement it, you would have just gone and said, okay, here are my widgets, here are my listeners. I don't organize the listeners in any particular way, and I'm done. Okay, I looked at Stack Overflow, I saw how our listeners are implemented, and I'll just write my spaghetti code. Okay, so you had to follow this discipline, which you may not want to follow. Okay, so I did say that, look, I can have automatic model sharing, but that means you have to find the model first. And again, you have to make a decision about, what the coupling should be. So why and what should it be is the other two. And one of them has to do with the programmer effort. And even when we did shared models, we didn't do a very good job. Okay, we said, we can have broadcast methods, but then we get into messes of, does one broadcast method call another broadcast method? You guys are having trouble with just a single user application, with cycles such as these. And the multi-user application increases the problem. I showed you sync, but it makes assumptions about the model, about certain patterns you use. So model sharing is maybe not the best thing. Not all programmers are aware of or care about model interactive division. Okay, so for the 401 students, I've taught you guys model view controller, and I suspect that when you went on and had to implement applications after that, you just did what was most convenient. Okay, so in fact, I want to do a little study of how much whether people really follow it on their own or not. And it's interesting. Last semester, I decided to put my 401 notes as videos. I was able to finally use the video conversion facility. And so obviously the students in my class, I did it at the end of last semester, so it was like in early December after Thanksgiving, so there was only so many days left. So students in my class before the second midterm did use it. But YouTube tells you, how many hits you're getting. And my most popular video is model view controller. So, and I wonder why. And then I just went and looked at search terms people use, and all these mobile phones force you to use model view controller. So it is actually, even though many programmers left to their own devices don't use it, some of the infrastructure that are coming around now are requiring you to use it. So maybe this is not a good reason. Okay, but still, like I said, if you were to build a desktop application, you would probably not care about it. Okay. So that's the programmer. What about the end user? The end user, if I have application independent coupling, I don't have to make any guesses when I go and use an application. I just know what I'm getting. Whether it's good or not is different, but at least I know what I'm getting. Okay? So you can make that argument also. So the question becomes how to define it in application independent fashion. Okay? Mapping between input and local feedback is application dependent. Whether I use model interactor, I don't use model interactor, that function is up to you. So how can I define coupling in an application independent fashion? If the local feedback is application independent, the remote feedback is maybe also application independent? Or can I put some constraint that is application independent? So if sorry, I really meant that if this is application dependent, then so is the remote feedback input function. So can I make the coupling somehow defined in an application independent fashion? Can I maybe define the coupling function as composition of two functions? So the mystery I said that a user has is, when am I going to see the change remotely, and what exactly is the form of the change? And what's the simple answer to both of these questions? So you type, you get some feedback. Now I have to figure out what my feedback is, and I don't know what that feedback will be, or I don't know when the feedback will come. So a simple answer to the question as to what my feedback is might be the same as your feedback, whatever that is. Okay, so we'll say it's two functions. First, you figure out what your feedback is, the inputter's feedback is, and then we go and say, after that, the remote feedback is identical to the local feedback. And now you see why that acronym was needed. What you see is what I see. That's my coupling. Okay? Question? No. June? Okay. So it seems to imply that the mapping between input and remote feedback is also application dependent, but not really. The relationship between local and remote feedback may be application independent. It may be dependent or independent. Okay? And so what you see is what I see. Okay? And in the last slide deck, when I was talking about broadcast methods, I referenced this paper, and I told you guys that the broadcast methods were used to build a host of applications. And so this paper is a really great paper. And it has those applications and that abstraction. And I believe this is where the word WYSIWIS the acronym was first coined. Okay? And so you see here that, actually it looks like I forgot a little square here. So these three displays are supposed to be identical. Okay? So remote user sees everything local user sees. And when? As soon as possible. We talked about that last time. Okay? We can't guarantee instantaneous. There's the speed of light we have to worry about, if nothing else. As you go from Australia to the US, that's significant. That's noticeable. The delay is noticeable. So if interaction stopped, remote user will eventually get feedback. Okay, that's sort of one definition. But you want to say remote user feels collaboration is real time. So you do the best effort to give immediate feedback. Okay, you send the stuff out on the router, and you just hope there's no queuing and so forth. Okay. Now, so there'll be some delay. Do you guys have any idea of how much delay is perceptible so that people feel it's real time? So when you interact with the website, sometimes it seems slow, sometimes it doesn't seem slow. We know it. There's always latency. So when can you tell that there was a delay? How many seconds, milliseconds, nanoseconds? I don't know.
milliseconds.
Did you just guess that, or?
Uh, it was a guess. I think we talked about this earlier in the class.
Yeah. 100 milliseconds is one answer. 50 milliseconds, some people think, yeah.
I think you said it was like 300.
No, so there was 30 milliseconds is the frame rate. 300 milliseconds was the delay from India to the US. Okay? You can notice that. Okay, trust me. But the 100 milliseconds is the time that some people say 50 milliseconds. That's sort of a discrete output. But when things are going, so when things are supposed to go continuously as in a video, then 30 milliseconds is what people think. Okay, 30 frames a second, right? So that's if you're doing less than 50 milliseconds, you're just fine. Okay, and I mentioned to you guys that in operating systems, there is your processes will execute for a time quantum before they are switched to another process, and you're supposed to get the feeling that you're getting continuous feedback. And again, it's interesting that the time quantum people choose is 100 milliseconds. The time quantum you choose is a function of how fast your computer is, because you don't want to be spending all your time switching between processes. You want to be doing real work. So as processors get faster, you would think that the time quantum would become smaller, but no, the numbers I saw in 80s are the same as the numbers I see today, because I think of this human thing that if you do it with every 100 milliseconds, it seems as if you're time sharing and you're fine. Okay? That you're not time sharing, and you've got the whole computer to yourself. Okay, so that's our constraint. Remote feedback is equal to local. Okay, the strict WYSIWIS coupling. Okay, I'm implying here that maybe strict is too strict, it's not too good, it's not as good. It means that if I move the window moves on your screen also. Okay, if I scroll the window scrolls on your screen also. Okay, by the way, these animations were created by one of my students. I'm not good enough to do these. Okay, but that's strict WYSIWIS coupling. Okay, I said this is well defined. It's application independent. Now, is that something you want? At least in some cases. So, what are the cases you might want this coupling in? What cases you might not? Now, this is an exam-like question. Trade-offs. What's good? What's bad about WYSIWIS coupling versus model sharing? So, what's good? It's application independent. Okay, that's good.
Now every user is seeing the exact same thing. There's a definitive, authoritative, this is the video.
This is the thing. There's no mystery. If I say that left window, there's referential transparency, if I want to use some big words now. Okay? And you can easily collaborate. Okay? And so that's a good thing. Bad thing?
The other user may not want windows to be moved.
The other user may not want the window to be moved on top of his email, which he's actually looking at and not bothering about the real collaboration. Right? So if you move the window on my top of my email, what will I do? Maybe I'll move it somewhere else. And what will you do? Maybe you move it back. So these guys who implemented WYSIWIS coupling, okay, window and scroll wars. Okay, you scroll it up, I scroll it down. Okay, and when we want referential transparency, that's fine. But when we don't want it, we're getting into wars for no reason. Okay? Size and view wars. Do I want to go and show this view or that view? Do I want the window to be this size or that size? Okay. And like I said, we are having these wars even when we don't want to share, perhaps. Okay, so when we might want multiple views. In an IM application, we don't want identical windows, right? We just want the content of the IM to be shared. We don't want an exact same display. So if in IM we don't want, IM is a very realistic situation. What's a situation when we do want this? Some application, some user tasks. Can you imagine? Remote control? So that's just one user. Or why? So why is some other user taking control of my computer?
Shared desktop.
Shared desktop. And why am I having a shared desktop? Receive help. Okay, I've got a bug here. Okay, let the Microsoft guy come and help me fix my blue screen problem. No?
If you have like a remote desktop sharing software that can share a blue screen, that's impressive. Keeps running and the operating system goes down.
Actually, it's very interesting. We guys did, for software engineering, we did a side-by-side programming experiment where I have two screens. I have my screen where I see my actions, and then I have another screen where I see your screen. Because supposing I'm helping you, that means my screen is now obscured by your screen, right? So I can't do my work, and I can't help 5 people at the same time. So what we were talking about was a variation of pair programming, where I'm programming on my screen and I'm seeing on another screen, physical screen, what you're doing. Okay? And I can see what you're doing, you can see what I'm doing. So we ran some tests, and one of the person's computer blue screened, right? And what did those guys do? They just started using the other person's actions because they were in sync. They were being synced through the model. So they were writing a program, and they just started, there was a fault tolerance for that reason, because you had two computers and they were both doing model sharing and doing window sharing. Okay? So maybe that's the kind of situation you're dreaming about. Okay, so the pros are it's easy to understand. Okay, it's application independent, and that means it's automatable much more than the model sharing. Model sharing says you go and divide your application to model and view, a model interactor, and if your model defines certain constraints, I'll share it. This one says do whatever you feel like. Spaghetti code, good code, I'll share it. Okay? And that's the kind of thing you're going to do in your next project. Okay? You're going to take your same application, share it another way. In addition, I'll give you another application that I've built, and you use the same infrastructure to share both your IM tool and the GUI that I'll give you. That GUI is already in that collab teaching project. Okay? And but let's go and say that we are not doing this remote desktop troubleshooting. We're really doing some work. We are maybe writing outline together. Okay, that's what the Xerox guys, that was their favorite application. That brainstorming some ideas. Let's say I'm brainstorming with you guys ideas for the exam questions. Okay, and everybody says, okay, these are the good topics to talk about, and then I'll choose later. So you'll come up with some ideas, and I want your change to be seen, and I want to talk about maybe the left change on top. Maybe we'll visually display them in a 2D space. So are some WARs worse than others here? The first example you came up with was that my windows, I don't want my window to move when your window moves. So how much will I lose out in this application if my window that is showing you the brainstorming session is at a different position on the screen than your window? Not much, right? I mean, we're not going to talk about the left window and the right window. We're probably sharing only one window. So maybe window sharing we won't do. Scroll sharing, yeah.
I feel like scroll sharing is more important because it makes sure that everybody's following along
on the same page, right? And scroll sharing, we can't avoid scroll sharing. The solution I'm giving you is very hard to avoid that. It's easy to avoid window sharing, just as well. Size and what about window sizes? If scroll sharing is important, is size sharing also important maybe? Because scroll sharing, you said we should see the same thing. If it's clipped in my window and not clipped in your window, again, we don't have that referential transparency. Okay. Again, size sharing is something we can't avoid in the implementation I'm going to talk about. Okay. But the same argument, view sharing also, that if I'm seeing a pie chart, you should also see the pie chart. But maybe the windows, window movements at least don't have to go across. And I'll go in more depth, I think, in the next slide. So window positions, yeah, we don't have to share that maybe. Again, if I'm actually troubleshooting, I may talk about the left window and the right window. I may want to talk about that if I'm troubleshooting some desktop problem. Okay, but if I'm sharing a particular application, then I want to only share that application's windows. And who cares whether those windows are positioned in the same place or not? Okay, we know what windows we're talking about. Okay. What about screen pointer? So right now my pointer is this little thing, but every screen has a screen cursor, right? You move between windows, that moves. Is that something that you should share? No.
No.
If I have, why?
That would be the worst for.
That'll be the worst for. I can't even do anything. I mean, I can't even reboot my computer. Right? You'll just move it away and say, no, you're not rebooting. You're not checking out. So what do I do then? How do we point? How do I say this idea stinks? Or this idea is wonderful? How do I?
Maybe you could highlight the UI was covered up or something like that instead of.
You could highlight it. Because that's very application specific, right? I mean, how do I highlight a little slider versus text?
Could we give each user their own pointer, and so the other user's pointers show up as glowing dots, and you can't move them, but you can watch them move.
Okay. We give each user a pointer that is separate from our screen pointer. And that pointer moves not only on my screen, but on your screen. And so that pointer is a telepointer. Telepointer. We've seen that in our examples. I did a very lazy implementation where we all had one telepointer, but you can imagine having n telepointers colored differently, labeled differently for each user. Okay? So we're going to have a telepointer in your next project. Okay? So when a mouse moves within a window, okay, so do you want those mouse movements to be reflected?
Well, you want your teleporter movements to be reflected.
You want the telepointer movements to be reflected, right? Good. But telepointer is moved by dragging it, right? So there is mouse movement, there is mouse click, and there is mouse drag. If you look at your tools, there's mouse motion event, there's mouse click event, mouse pressed, mouse released, mouse clicked, there's mouse drag. So telepointer we want, because that's mouse drag. But if I'm just moving the mouse around, yeah.
Well, how is mouse movement from mouse drag? Is mouse drag when you drag a window or something?
When you
Okay,
click and
so
move.
drag.
So at that point, we know, the hardware knows that some button is clicked and the mouse is moved. So it takes those two events together and gives you the event that your mouse is dragged. Okay? And the mouse drag, I'm just a fidgety person. I might be moving a lot, and a lot of traffic might go across the network. Okay? A lot. And when you're debugging and something's going wrong, something goes wrong very badly. Okay? When this happens. So maybe just pure mouse move we won't send. Okay. What about window borders? Do we need to share those? Okay. What about window sizes? Sorry, window sizes we saw we needed to share, right? Okay. And as it turns out, when you if you're doing something in an application independent fashion, the program, if you're sharing one logical program and the program is working at the window level, which is sort of what we're talking about here, it has to assume a certain size of the window, or it can assume. Okay? And then we have to share that. The window borders, the same Java user interface, Java program that you execute, looks differently on your Mac and your PC, partly because the text boxes and so forth are different, but also looks different because your window borders are different. And can I have different window borders on a PC or on a Mac? You can. How do you guys do it? So can I choose what kind of window borders I have?
Yeah.
How do you guys do it?
Java API, you will distinguish which system you are using, and it will display the folder for the system.
So you think it's a Java thing that each program can decide? Has anybody done it? Have different window borders on your computer?
It's a Java feature.
It's a Java feature?
Set look and feel.
Yeah.
That look and feel, really? And what does it do? It changes the way the borders are?
It changes all the interfaces.
Okay, so that's different. What's inside the border, what's inside the window is one thing. What's on the border is another thing. Borders are important for why? Why? If a window didn't have a border, would you be in trouble?
That looks weird.
It looks weird. What about action? You can't close it, you can't move it, you can't do anything.
You
Okay.
can still close it by pressing Alt plus F.
Okay. So you need to know all these keys to do that stuff. Otherwise, you couldn't do it, right? So what goes on inside the window is what your Java program displays. What goes on outside the window in the border is another program. Okay? And I know, the reason I ask you this question is because I don't know the answer in today's world. But in my old world, we could change the borders. We could just run a different program that draws different kinds of borders around the windows. And I believe you can still do it. I just don't know what the exact way to do it is. Okay? So window border doesn't seem very important. Who cares how I move the window, how you move the window? Okay? Key click, mouse drag, these all seem important. Okay? So we are going to go towards not strict WYSIWIS coupling, but near WYSIWIS coupling or relaxed WYSIWIS coupling. And these guys who built the first such interfaces, they wrote another paper, WYSIWIS revised. They came up with WYSIWIS and said how wonderful it is, and then they said, maybe not. And from what I know about them, they didn't write the third paper, which was, we like the original idea. The revised wasn't that great also. So there's been a big debate, and I came after them. And my claim to fame was the first paper I wrote on this was something called flexible coupling, which is that, hey, it depends, and here's a little way to get all couplings you want in one system. And so that sort of solved that problem. Or at least address the problem to some degree. But window positions, we're not going to share. Okay? Different window sizes create ambiguities, cropping, scaling, and scroll synchronization creates referential transparency. So we're going to go and share the window size. We're going to, we talked about these things. Screen pointer is problematic, we just saw. And it doesn't have much meaning if some windows are shared and if windows are moved independently. So the question is how to point. We're going to have a telepointer, which is a shared shape, possibly per user, that can be dragged over any part of a top-level window. Okay? That seems like a very nice abstraction, where we're going to just have a telepointer that works for any application. How to implement it is tricky, but I've done a lot of the work for you, so for you guys, it's going to be easy. Okay? Okay, screen pointer we won't share. Window border we won't share. Okay? And so the next question is how to automate WYSIWIS or near WYSIWIS coupling. Okay? And in general, when you're automating, and I've said this before, I'm just going to repeat it, is that you're going to have some application-independent infrastructure provide the functionality for you. Okay? So of course, when you use a programming language, that does things for you. When you use a toolkit, that does things for you. And so it automates widgets. The sync system I talked about automates sharing, model sharing. And whenever you automate, you make some assumptions. Okay? And, so in these toolkits, they assume that you're not going to have round widgets. Okay? And you say, you know what, I'll live with that. I don't want to go and implement round circles and round widgets. I don't want to do that work. Okay? And in sync, you assume you want model sharing and not interactive sharing. So we need to make similar assumptions if you're going to do WYSIWIS. Hopefully, the assumptions are not as strong. Okay? And as we are not doing model sharing, we're going to have to share the state inside your interactor. If you built an interactor. If you haven't built an interactor, it's something inside your application that has to do with I/O. Okay? And So to do that, I need to access somehow the input and or output. Okay, so I have to now tie myself to some user interface abstraction. Okay, when we were doing model sharing, I tied myself to write methods and ways of declaring write methods. I needed to get into the programming language to intercept those methods and to inject those methods in. Now I have to go and tie myself to some I/O system. Okay, so there's a lot of research being done in this area, depending on what I/O system somebody tied themselves to. And they said, look, if I use X, which is a Windows system, or one kind of Windows system, this is what happens. By the way, the seminal paper, or at least maybe I'm biased, a very important paper written on X sharing was done by somebody here, somebody you guys who are undergrads know. Anybody want to guess? Not me. Systems guy. So Kevin Jaffe did one of the first papers. No, I shouldn't say first papers. One of the nicest papers on this thing with a guy called Hussein Abdul Wahab, who was visiting here. So those two guys did this work. So at one point, this university was a very big collaboration, and I was at Purdue working alone. So I said, hey, I'll join this group, and so that's how I came here. And some people retired and moved on to different areas. Okay. So you have to assume I/O can be tapped, and assume certain properties of I/O. And so what we're going to do is the following. I talked about intercepting events and method calls and injecting method calls. Now you have to intercept I/O calls. So what we're going to do is we're going to take some existing I/O system, some I/O system we did not build, some I/O system that is not probably open source that we can change, some I/O system that we'll keep collaboration unaware, okay, which could be the X window system that I talked about. Okay? And I'm going to take some application that is built on top of that system that also we can't change. Okay, these are very strong constraints. I want WYSIWIS coupling, I want a lack of awareness, but you can't not have awareness at all in the system. Otherwise, how are events going to go from one computer to another computer? Okay? We're going to create a proxy in between. Okay? Just as we created a proxy model when we were doing model sharing, okay? We're going to create a proxy here, which could also cache things. And you see how it's colored carefully? So to the collaboration-aware application, the proxy looks like the system. Okay? To the system, the proxy is the client. Okay? So it's got these two shades, blue for one system, white for another system. Okay? And we're going to just do some magic there to provide collaboration. Okay? So that's a general principle. When I talked about, there are all these systems that take different I/O systems and build collaboration around them. They differ in what this system is, what this application is, but the principle of having a proxy applies to all of them. Okay? I'm just repeating what I said. Okay? So there's unawareness. The awareness is all concentrated there. Okay? And proxy will be the one that distributes the I/O. So much like, sorry, not line, in shared model system. So I said all this before, I've just got this in text. Okay? And then the question becomes not only whether I should use the X window system or the V window system or some other Microsoft window system or the Mac window system or the Android window system, but should I use a window system? Should I use some other layer? We have to do something within the interactor. We've decided that. The interactor is really not only the code you wrote, but all the code it drives. Okay? So should we go and do something here, 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 here? If we do something here that's application specific, we're not getting automation. Okay? And there's these 4 levels of abstraction we saw. Frame buffer is the whole frame buffer. Okay? Frame buffer gets divided into windows. Each window gets divided into widgets. And a widget can be a particular form of widget, which is the console widget. So then the question becomes, which of these 4 layers should we go and tap to build our WYSIWIS or near WYSIWIS coupling? Okay? So any suggestions here? I'm kind of implying Windows system, but why Windows system? Maybe that's not the right thing. So what's wrong with just doing console, tapping the console I/O? So let's just answer one by one. So console application, you read some line, you write lines. Nobody's done that. I thought about doing it once. I forget whether I did it or not. Actually, I did do it a long time ago, but not very useful. Actually, I remember now, we built a multi-user command interpreter, a multi-user debugger. These were all these text tools. Okay, they were shared. So yeah, we did do it. With a bunch of undergrads that did that. Why am I implying it's not very useful? Are we getting near WYSIWIS coupling here? If my console window moves, will your console window move? If I scroll, will it scroll? Is there any scroll events being passed between? The proxy is just getting reads and writes, right? All it can do is distribute the writes, or so it doesn't know about all those events that we were talking about. Okay. So, but it's an interesting idea. Can't handle GUIs. Okay. I press the widget events you guys are aware of now. Okay, your document listeners, your action listeners. So I press A, the collaboration unaware application gets text changed. It goes and says set text. If I tap these events, could I do my job?
So you can't. There's something in the console. You can only control the GUI.
So how do you control the GUI? So you're saying how do you control, meaning you move the window?
No, just send text.
Okay, so that's what you can do, right? You can send text, you can send slider movements, you can get this, you can insert characters. And is this going to work? If console one didn't work, same reason this won't work in many cases. Sure, every time I type a character, if I have a document listener, that character will get changed at the other end. So it's better than console. But if I go and move the window, okay, it won't move. If I resize the window, which is something we want, the resize of the top level window is not a toolkit event. Okay, so you have text box, sliders, and buttons. Now this may be the coupling you want, but it's not WYSIWIS. Okay, and it's bound to a specific toolkit. Okay, there's swing, there's AWT, there's SWT. If I go and choose SWT, the swing guy, the swing guys can't use my facilities. If I use swing, the SWT guys can't use it. Okay, the GWT guys, which are the Google guys, can't use it. So cannot be used to share state that is the window state that is not kept in the toolkit, like window size. Okay, so maybe not. Okay. And it cannot be used to share collaboration unaware window apps. So I might go and create an app like this, which just bypasses the toolkit layer. I've got this, this application where around the current cursor position, I draw a bar and I draw a circle and I draw the character. Okay, useless or useful widget, we don't know. But that's my stuff that I built on top of the window system. And you can't share this. Okay, for the same reasons you can't share SWT if you're doing swing. Basically, you're bound to one widget set. Okay, so we won't do it here either. Okay, this means that you guys who've been working in the toolkit layer will now need to work at a lower level layer to do the sharing. Okay, and you have to learn this lower level layer, which is a little abstract in your head right now, but by the next assignment it will be more clear. Okay. What about frame buffer? So window system is what I'm targeting. Let's go down to just the whole screen. So screen, what is a screen I/O? If I press A, it'll tell the application that's listening to frame buffer that A got pressed at coordinates x and y. And what do these x and y mean? X and y relative to
The entire screen.
entire screen, not the specific window. So I can do a lot with this, by the way. In fact, real systems use a lot of this sharing. Can I do exact WYSIWIS with this? Yeah.
What, if we have different size screens?
If you have different size
places,
screens.
then it doesn't-
You know, I had a student do a project on this. Oh boy, he sweated and sweated and sweated to make this all work well. Okay. So if you have exact, if you know, and you know, what about just the restart menu, but restart region? You know, where do the lower left corner where you reboot things, that just had different meanings. So it becomes tricky. So you use some elements of it, but you know, now you're forced to share the screen pointer. Okay, you can't have your private window reading mail. So you can have pure WYSIWIS as long as everything is identical. And then when I reboot, you will reboot too. Okay. So what you draw is, so your output operation is drawing a pix map. Not draw a line, draw a character, just calculate the bitmap and draw it. That's your frame buffer operation. Okay. You're forced into WYSIWIS. I forgot an I here. No private windows. Okay, no heterogeneities. But commercial systems tend to go and combine. What's nice about this? That I don't have to worry about what Windows system is running there. I can build a VNC system that works for Macs, for Windows, for Unix systems. And you know, that's a very popular sharing system. So that is nice. I don't have to go and, the system you guys will build is going to be tied to the Java window layer, okay, which is, you know, which is nice because it can map to the Mac window layer or the Windows window layer, but it's not as universal as something like this. Okay, so we'll talk about how to go and combine shared window and frame buffer, but for now we're going to focus on the window system. Okay, so our window model is very much like our frame buffer model. It's not talking about widgets and not talking about, you know, sliders and text and document listeners and this whole bloated API that toolkits provide. Okay, very simple, relatively simple API. So you get key events and mouse events. You get coordinates relative not to the screen, entire screen, but to the window in which the action occurred. Okay, so at any one point there's a focus window. That's the window you are interacting with, and actions occur relative to the focus window. Okay. So what are windows? They're untyped rectangular screen areas in today's systems. Whether they are text areas or text fields, the window system doesn't know. Input indicates keyboard and window mouse operations with window relative coordinates. Output draws various kinds of shapes, not pix maps. And your application is the programmer-defined code that you wrote, plus the toolkit it's using. That's, to the Windows system, they're both the application. Okay? And window-level automation accommodates all toolkits and allows private and public windows, which are important. So now the question becomes, okay, we're going to choose this. We're going to put our proxy here. The question is, what is this proxy doing? And this has one user. This is my computer, my window system, my proxy, my application. What happens when there are n users? Well, how does this picture change? So that's now I've told you enough background on what we're going to build. Now let's get into the collaboration issue. So I want a window on my screen to mirror the window on your screen. I want a logical window that is shared, that's physically replicated. Just as previously, I wanted a logical model that was physically replicated. So how do I, you know, what kind of diagrams should I mean, we'll spend some time with the algorithm and the architecture. but intuitively, how does this picture change? And is the picture symmetric on every user or asymmetric on asymmetric? So just the first things that come to mind.
Different users share one proxy.
Okay. Different users share one proxy. That's tricky because the proxy is the one that's doing the distribution, right? The proxy is the one that takes events and sends it across to another computer. So if it's going to send, if your proxy is going to send events to my computer, I need something to receive the events. My Windows system can't. My application can't. So I have to have a proxy on each computer. So that's a given. That we need a Windows system on each computer for sure. Otherwise, how am I going to show the window? I need a proxy on each computer, at least to receive events, maybe to even send events. Yeah.
But the application could just be running on one computer, and the proxies hide that.
It could do that. That's an asymmetric picture. That's like my centralized model sharing. When my model is on one computer, my interactors are replicated. That's one answer. Another answer? What's the opposite of that? So we had centralized model sharing and we had replicated. So what would replicated window sharing mean?
It would mean that there's a copy of the application running on every computer and they're kept in step.
They kept it step. What do you think you'll be doing in your project? You don't know. Or what do you think intuitively?
How many machines are we going to have for our project? Are we going to need to set up so we get this working on multiple machines?
Since we are doing window sharing and not desktop sharing, we can run it all on one computer, which is what my demo showed you. If I was doing screen sharing, that would be a problem, right? Actually, there's ways we have virtual desktops, which I'll talk about. So you can just run it all on one computer. But I mean, your program, the one you wrote for your second assignment, will just work just as well on two computers. You just have to go and change your server location. Okay. So, so the question is, and we don't know quite the answer. What do you think you'll be doing in your project? Running it all on one or running on multiple? And I wrestled with this question, what I should give you. And then I tried various alternatives. And the most general solution I could come up with, which depended on what I could go and tap, whether I can intercept input or output, I can inject input or output, was the replicated system. Okay? I came up first with centralized, and then it had some problems, and then I found a way to do replicated. Okay? That's not how commercial systems work. Okay? But that's how we're going to do it, and that is a valid answer. So we're going to okay, so I guess I'm getting into I got ahead of myself. Before we talk about intercepting window I/O and go to the replicated system, which we will do soon, okay, hopefully before the class ends, let's talk about what I/O really is, Windows system I/O is among the various events we saw here. So when the key clicks, the mouse drags, that's window I/O, right? Clearly from what I said. Mouse moves, that's window I/O, which we may decide not to send. When the window size changes, when the scroll position changes, is that window I/O also? Scroll bar changing, is that window I/O?
Yes.
Yes. Windows are untyped rectangular areas. A scroll bar is a rectangular area on the screen that is typed. What's going on underneath? When you move the scroll bar, what are you doing? You're dragging the scroll, quote unquote, some rectangle within that rectangle. That's your widget. Okay? That's your toolkit. So this is toolkit. When the window size changes, would you consider that as window I/O? Yes? When the window position changes, is that window I/O? Why are you distinguishing between, why do you think the window position is not window I/O and the window size is window I/O?
Since you drag the window to change the size and the position, and it's not important.
It's not important to the application. So the application may care about the size, so that redraws. The application may not care about the position. Okay, good. So as it turns out, let's go and look at who's managing these things. Okay? And this comes back to my being able to change the border. Window positions and sizes are events that are detected not by the window system, but by a window manager. There's a window system and there's a window manager. When I can go and change the borders of my windows, and in Unix systems, I could have a running application and just kill a window manager and start a new window manager, and my borders will first get deleted and the new borders will get put. And I'm sure you can do that now in new systems too. Okay, that's a window manager. That's a separate entity. Okay, and the scroll position is the toolkit. Okay, so I just want to be clear that what is window I/O, what is not window I/O. But yes, the application should know about window size changing and position changing. So the picture, there's not only a window client is a client to not only the window system but the window manager also. The window manager does not go and handle key clicks and mouse clicks. It handles higher level events. Window moved, it provides a way for you to move the window, for the user to move the window. When the user moves the window, it goes and tells the client, hey, the window moved. And why would a client, you just said, it's not important for the client to know about window movement. Can you think of a situation where it's important? So what these systems did was they not only told the window client the window has moved, they also asked the window client, is it okay for me to move the window? And the systems you guys use, how does it matter? Way back when there was research in Windows systems, as far as I know, got invented in Xerox, okay, like many good things. Or maybe Douglas Engelbart did that too. I don't think he did. And there was big debate between overlapping windows and tiled windows. Overlapping windows are like my desk and my physical desk. Everything is over everything else. Tiled windows are like neat desks. There's a pile of papers here, pile of windows here. You say, this is my teaching stuff, this is my research stuff, this is my private stuff. And people said, and so the way the window system, Xerox guys invented the notion of a desktop metaphor. So, your Windows system should reflect the physical desktop. That was a big deal. And then they talked about the clean desktop. And researchers in academics loved the tiled windows. Why? Because then they could solve constraints to automatically arrange the windows. There was some computer science to be done. Overlapping windows was such a stupid thing. Wherever the user moves the window, it goes. Okay? As it turns out, tiled windows died a very quick death. Not in research, but eventually even in research. Okay? And so that is the reason why even these events were sent to the window client. Okay? So the window client can at least be told that the window is here. And it can also go and ask for the window to be moved. That's important. It can, just as you can say, please go and move, output this character at this position on the screen, it can say, please take this window and move it here. Okay? And sometimes when I do demos, I use that facility, right? I go and take this window and move it, I position it here, I move another window here. So this is something you can do in Java, set position. And window moves. So here the input is window move, resize, user operations. These are the input events you get. And the output is you move the window, you resize it. Okay? A window manager is conceptually separate from window system, and you can change one without changing the other. Okay? It's often a separate modular process, at least in the old Unix systems. And it puts decorations on window for moving and resizing. That's your window manager. Okay? The picture is that your window client is really getting events from both the window manager and the window system. It's producing calls to both, and the window client sometimes doesn't know the difference. It's just outputting these things to a common object, at least in Java. But that's what's going on. Okay. So now I'm going to answer the question: how do I go to end users? So we're going to, in my picture here, this proxy is representing both the window manager and the window system. Okay? And I'm going to be very loose now and talk about that being the window system. So what is the architecture with end users? Here's an architecture that mirrors what you guys have done in your replicated models. This is an architecture that is easier to implement. So the user presses A. The event is captured by the input distributor, okay? By the proxy. I'm calling it the input distributor. This is the proxy. So to this system, this is the client. So it tells the client, hey, A got pressed in window 2 at XY. And what's the proxy going to do at this point? Tell other proxies and
the actual application.
tell its client. Okay, it forwards it some level of indirection. That goes and makes a draw call through the proxy, and it goes and tells the other proxy, which goes and tells the application, which goes and draws. Nice, clean system, symmetric system. Not too hard, right? One day's work for your project. Even changing a little, one line of code is sometimes a day's work because you don't know what to change. But anyway, that's a basic idea. And the second basic idea is, okay, how do I know that this window corresponds to that window? Now, every window system has got its own window. Okay, I've got window number 10 here. You got window number 10 there, 15 there. How do I make sure that 10 and 15 are the same thing? We saw the same problem that occurred with replicated model sharing, and how a corresponding window is found. We'll assume either that the application is the same one running at all ends. We'll assume that the windows are created in the same sequence. Okay, so you'll have to worry about this problem. This is not just a theoretical problem to be studied for in the exam. And you can also assume that every window has a name. So I think in the demo application I will give you, every window does have a name. The windows you create, you can also give them a name, and you can use name correspondence also. It's up to you. This is going to be more general. It doesn't assume that names are given, but it may be flaky because of threading. Okay, so this is a problem you'll have to solve. So theoretically, conceptually, the two biggest issues you have to face are easy, relatively. I've told you the solution. Okay, that you have to distribute the input. Now you saw why that proxy was called the input distributor. All it did was take the input and distribute it to other proxies. Okay, the output went directly through. It didn't have to go and intercept the output. That's why I didn't have two boxes for the output. And you write an input distributor with your couplers, and you go and have to build a registry of some kind in your application that goes and keeps track of what the global ID of each window is based on sequences or names, and you translate between those two things. Okay, this is not going to be that easy. Nothing's going to be that easy, but conceptually, this is what's going on. Okay, and we'll go look at the algorithm next time. Okay, so what happens here is the user presses A, let's say. The input goes to the proxy. The proxy goes and gives it to the application. So this is just as you would, that's just as what would happen in a regular system. And what we do in addition is send the input across to other sites, and the input is received by this special agent that we've written, and that agent just takes the same input and sends it to its replica, which hopefully will produce the same output, and we're in business. Okay, that's the basic idea. And it goes to the other end too. And notice the window identifiers. So you pressed A here. A was pressed in some window that 2 that this particular system knows about, window 2 in this system. And this is user 2, so I call it window 2. And the actual physical window that is displayed on this system is some other window, say window 1. So we have to go and translate between window 2 on one system and window 1 on the other system. Okay, so that's a little complication. So what we're going to have to end up doing is sending across the network not window 1 or window 2, because that doesn't make any sense to the other system, but some window I, where I is some global identifier of the system. Okay, so that's the basic idea. Okay, so let's go and look at the algorithm, and the system is replicated. So the algorithm should follow pretty much what was done in the replicated model case. In the replicated model case, there was an input I, and we went and found magic edit input made, notified, observed, and so forth. Made was the key event here, and this edit sent basically sent the edit made across the network, which was received by the receiver, which then went and did the edit at the local replica also, and then of course a chain of events followed that. Okay, so how is this going to change in the window system case? What are we intercepting?
We're intercepting inputs from the users, so it's not really edits that we need to be notifying each user of. It's inputs that
It's some lower level input. This input I was a higher level input. It is some lower level input, the input that the window system creates. Okay, so we're going to so we're going to also create a telepointer. Okay, we saw that last time, that we can't go and just share the screen pointer, okay, because the screen pointer will go over private windows, public windows. So we're going to create a telepointer. That's one thing. And for each window input I, including the telepointer input, right? I should be followed by matching window event dispatched. Okay, so what's going to happen is every input is dispatched by the window system to the application. Okay, so dispatch and processing are different. Dispatch is what the system does. It says, okay, here's an event, I'm going to dispatch it to my client. The client can then process it. Okay, so the window system can't guarantee processing. So it's not going to wait for processing to finish and doesn't even know about processing really. So it says, okay, I'm going to take this input I, I'm a proxy. I better do what the original window system did, which was to dispatch to the client. Okay, plus I should go and just send the window event across. And for every window event that's received at the other end, you go and do a local dispatch, translating the windows. Okay, and we make sure that that doesn't cause a redispatch back to the original site. Okay, so that's the basic idea. And what's this transmit I that I've put in here? So why put a little filter here?
there might be some events that we don't want to send.
Some events we may not want to send, like the screen pointer, like a window move. Okay, so we are going to do this in the model case. Also, we might have some private fields, private properties in an object, which we may not want to send. Okay, but here there is more compelling reason for that. Okay, so window event dispatch is different from processing. We'll see that soon. And what really happens is that you dispatch the event to the client, and you may dispatch it to the dispatching may involve figuring out what sub window to give the event to, and then in the sub window making sure listeners are invoked. Okay, all that stuff we don't have to worry about. All we do is dispatch it, and the dispatch will result in appropriate dispatching. Okay, appropriate finding of sub windows and calling of listeners. Okay. So window system can only guarantee delivery, not processing. So dispatch is basically you're delivering, you're not really processing, and transmit I not all events may be sent, and we are doing relaxed WYSIWIS, and we saw the reasons for doing that last time. So that's what's happening. Questions? So the things that we are not sending, the transmit function, so what are we not going to send? We are not going to send window manager state. Last time I told you that there are two agents that are managing windows for you. One is the window system that's allowing you to draw things and get input. And then there's the window manager that puts a border around these windows and does operations that associate with the border, like iconifying the window, maximizing it, moving it. Okay, so that state we won't send. We won't send the screen pointer. Scroll positions are something that anyway we don't have to worry about. That's at the toolkit layer. So it's not that we won't send them. These events will get sent, but the window system won't send them. Window system will just send mouse drag, mouse click, key click, and so forth. Okay. So that's one kind of filtering. Can you guys imagine other kinds of filtering you might have? So given a window, I will send only some of the events relevant to it. Other kinds of filtering? By the way, if you regard window resize as a window manager state, then we will send the resize event. Okay, so this is maybe a little too broad, because resizing is something you do with the window manager, but that's something you really need to know at the other end. Okay. So if I'm reading mail and I'm sharing the IM application, do I want to send the events in the mail window? Okay. So we're going to have some private windows also. If I'm dragging the telepointer, do I want to send every telepointer event, every mouse drag?
That could end up using a lot of bandwidth.
That could end up using a lot of bandwidth, and that could cause a lot of problems debugging. Okay, and so, but you want to send enough drag events that the other person doesn't notice the difference. Okay. So we'll filter by event type, okay, for the specific window. Telepointer drag or generally mouse drag. Should we send all mouse drags or telepointer? So, we want the desired time between drag events should be 30 milliseconds or less, okay? And I once actually observed how fast the application gets drag events, and that was as fast as 10 milliseconds. So basically, every third event could be sent rather than every event. Okay? And you can slow this down even more. So that's something we might want to do. Okay, so in your next project, I'm going to make filtering of drags an extra credit feature. And those of you who want to do it can use this criteria. Okay? But the simple way to do this is to go and say, okay, if I've sent a drag event in the last 30 milliseconds, I won't send this drag event. And can you guys see a problem with just this simple-minded algorithm? What about the last drag event? Okay, you do want the telepointer to end up at the same position everywhere. Okay, so you do want to send the last one, and it's the last one when you receive a non-drag event after that. Okay, so that's something you have to worry about. So we'll filter by event time, and then the thing is send actions of all windows. No, you're going to have a mail window in which you're going to do things privately. In the assignment after the third one, you're going to do concurrency control. Concurrency control means that one user can request a lock. That doesn't mean that all users are requesting the lock. That means a lock event button press should not be sent to everybody. So that's something you'll need in your next assignment. So this filtering also you'll have to do. Okay. So filter by window. So what we'll do is we'll just say that these other windows have special names, and those names we will not filter out. Okay. So of course you're building this layer in the context of a specific JVM, and that JVM is not creating a mail window. Okay, so this mail example is for the cases when you're creating a system that works for all JVMs, okay, which we're not going to get into. But the locking window you will create within the same JVM, so this is going to be relevant. Okay, but in general, when you create a window system, you create it for all applications in the operating system, And that's a little bit more ambitious task. You have to deal with the operating system layer, and here we want to deal only with the Java layer because that's just easier. Okay, and we get all the principles. So that's the algorithm. We've got the block diagram. Are we done? And I said that it's easier to deal with Java, but it's not trivial. So there are a lot of system-specific issues that arise when you want to create this algorithm. This algorithm is not tuned for Java or any other specific system. It's a general algorithm. So we have to now worry about, in a specific system, how do we create a telepointer? Okay, creating a little circle and figuring out whether you are dragging it is easy. Okay? How to make sure that the circle is a telepointer that shows anywhere on the screen or anywhere in a particular frame, that's a little bit more challenging. Okay? How to intercept time? I said, in general, there is some event flow between the Windows system and the application, and you have to tap into it. How to tap? That you have to know. Okay? And once you've tapped an event and sent it across the network, sending across the network is not such a big issue now. You guys have done assignment 2. The question is how to inject it at the other end, translating between window IDs. Okay? And how to translate window IDs, how to even know what all the windows are in an application. Okay? Because we don't want to change the application. Okay? In the JVM, we'll create a little layer that says, given, we are going to share all the windows in this particular JVM. Okay? But that layer should be oblivious of the exact code written in the application to create the windows, ideally. Okay? So how to go and translate window IDs when you don't even know what windows are being created in the JVM, and how to filter events. Okay, there's some challenges there too. So that's what we'll do. Hopefully, we'll finish it all in the remainder of the class. So to do all this stuff, we're doing pretty advanced stuff for Java window systems. We have to learn about some basics of the Java window system to do this advanced stuff. So a side effect of this whole lecture is that you understand the Java window system better, and as a result, you also understand window systems in general a little better. Okay? So just as when you did assignment 2, you got to know about session management, I gave you a library, but you also got an idea of what the distributed layer underneath was like. Okay? So you'll get to know what the layer you're going to deal with is. Okay? So discussion so far fairly abstract, need a real window system to make it concrete, and we will use Java. Okay? So what Java does is Java hides the underlying operating system window layer from you. Okay? So it's going to work for Macs, it's going to work for, actually I don't know if it's going to work for Macs or not. So you guys, I noticed a lot of you guys deal with Macs. And if it doesn't work for Macs, just do your demo on a PC. Okay? But it should. Okay? Java is supposed to be portable, but this is where Java's portability reaches its limits when it comes to the Windows system. Okay? So in general, there are top-level windows and sub-windows. Okay? And the sub-windows in the window are also windows. Okay? They're also things associated with the mouse events, and the translation is done for you, that you're told that this mouse is in this particular sub-window, and you can just deal with that sub-window events rather than the other window events. Okay? And what Java does is create certain abstractions on top of the window system, where you have frame and JFrame, you have panel, containers, components, canvases, and these are just special cases of these windows. Okay? And from our point of view, they're all windows. Okay? And there's actually 2 ways to access the window system in Java, through AWT and Swing. Okay? And what's the difference from those of you who might have read about it or know about it between AWT and Swing? And just as we have multiple natural languages in this world, we have multiple layers. That's natural. That's expected. But why should the same set of guys create 2 kinds of layers? Okay, so one of them is native and one of them is pure Java. So there's JText field and text field based on these names, which is Java and which is native. So, okay, so this is swing, and this is, okay. So what happens is that you've got the Windows system from OS, okay, and one idea is to just go and put a little layer on top of these windows, okay. You get the same, you get the Windows system, the operating system's look and feel, okay, and this rectangle is really a rectangle understood by the underlying operating system. Okay. The other is to say, hey, operating system, you give me the top level window. That I won't deal with because you've got your window manager and you need to go and move them, resize them. I won't interfere with that. I might just make it look a little different, but your rectangle is my rectangle. Okay? But within that, I will go and take these rectangles and convert them into my windows. As far as you're concerned, these are rectangles in your top level window. As far as my clients are concerned, these are windows too. They look a lot from the API point of view as these other windows, but in the implementation, they are more lightweight. Okay, they're done in user space, they're done in Java. Okay, that's why there was Swing and AWT both. They came around the same time. Okay, so Swing Windows is truly an abstraction on top of the Windows system abstraction. Okay, it's taking a top-level window and dividing that into sub-windows. Okay, again, these sub-windows maybe sliders or may not be sliders. That's a separate issue. As far as we're concerned, they're just rectangular areas associated with mouse clicks and key clicks. Okay. So this is an OS window. This is an OS sub-window. That's a Java sub-window. Okay. So, as users, we can and programmers, we can worry about the Swing API is not identical to the operating system API, but it's very similar. So from a programmer point of view, there are these API differences. From an end user's point of view, there are these look and feel differences. Now we are putting on the hat of a shared window implementer. And intuitively, which do you think is more shareable? AWT or Swing? Swing? Because? You think AWT? Swing is more. Why? Why? Because Java, sorry? Oh, Java's portable, so maybe portability and extendability go together. Yeah?
Yeah, with Swing, if there's any differences in the operating system's implementation, Swing can kind of cover those up with Java.
Okay, so Swing covers things up. That's a key. Is covering up good or bad is the other issue. Okay? Because the more it covers, so Swing could do more than the OS guys. Swing could learn from those guys and do a better job. It's portable, but so that means it's maybe that goes with shared windows there. Anybody want to argue for AWT?
I mean, so the advantages though that you're talking about Swing also exist in AWT. AWT is abstracting away details too. You just kind of get the lowest common denominator of what.
Oh, so you may not get certain events through AWT. That's another thing.
Right.
Whereas with Swing, you will get all the events because it's all under the Java's control. With AWT, you may not get certain events. Okay. The fact is that Swing and AWT, despite, I really am annoyed at the Sun guys because, like I said, some of the people in my community were working with the Sun guys and they knew that one should go to sharing at some point. So the question is, were they thinking of injection and interception when they designed Swing? Okay, and to me, they were not. Okay, you guys dealt with that problem in the document listener, that if only you could know whether the event came from the application or the end user, you could do a better job. Okay, we know that somehow Swing is getting events from the Java is getting events from the operating system. Okay, it is intercepting the operating system events. So it could go and just take those events and allow them to be intercepted. Doesn't have to do extra work. Okay, so interception at one level could mean interception at another level too. Swing may not itself allow all events to be intercepted and injected. Okay, so that may be an issue as long as the OS is giving it all the events. And I just couldn't make, if you remember the demo, I couldn't make the JText field shareable because I couldn't get the caret position to move at the other end. Okay? Because Swing was doing some underneath some processing that I couldn't trigger off at the other end. Okay? That's why when I gave you the first assignment, I said, create this as a JText field, this as a text field, and there were pros and cons between the two layers. And on the other hand, some events may not be correctly interceptable or injectable from the OS, and I could not make the AWT checkbox work. Okay? Whenever I would press the checkbox at one end, I would see the checkbox flicker at the other end, but it would not get on, and I think I got 2 events other than 1 event that said turn it on and turn it off again. Okay? So there are these idiosyncrasies. I don't know whether they are because of portability or not, but this is my theory that, with AWT, some things were being done by the underlying operating system, and if you inject it back, Swing just goes and tells the operating system to do the same task, and so the collaboration occurs. Swing itself is not as good as the OS in doing this. Okay? So that is from the point of view of interception. From the point of view of telepointer, on the other hand, telepointer is something that should be drawable anywhere on the screen, and as it turns out, the telepointer, do you guys remember what happened to the telepointer? Was it drawn over Swing? Well, you can see it's drawn over the Swing area. It was not drawn over the AWT area because it was interfering with the telepointer. Okay, so telepointer possible over Swing, but not controllable, less controllable AWT windows. So telepointer abstraction is something I get from Swing, and that doesn't work for the native ones, AWT. Okay, so you're seeing very concretely some differences between these two systems. Okay, but we are concerned with basically taking an event, injecting it at the other end, and if that doesn't do the right thing, that's that system's problem. Okay, as long as we are doing it as long as it works for some components, it should work for all components, because all we're doing is taking an event and sending it across. Okay. Okay. So I could go and say, okay, guys, Google the AWT Windows layer, Google the Swing Windows layer, and do your job. Okay. But I'm not quite doing that. AWT and Swing created certain abstractions to create single user interfaces. As it turns out, those abstractions, and I had to do a lot of research to figure out how to do this, could be used to do some sharing, modulo the problems I showed you in the last slide. And to find all this stuff, I had to go and Google, I had to go and try things. And so it's nice that these mundane, stupid things that Sun should have fixed on its own, you don't have to worry about. So I have created a layer on top. Okay, so you have to worry about this layer now. Okay, just as you had to worry about how the communication library worked, you have to worry about how this library worked, and it's not got a big API, and the API is my class lectures. Okay, so please do follow what I'm saying, and I'm giving that in great depth. So it's to hide messy details of AWT and Swing. Okay, so that's what we're going to work with, and the library, of course, mirrors what's happening underneath in the Java system. So let's try to understand how these pretty boxes, or these simple boxes, I won't call them pretty, really translate into Java API calls. Okay, and let's focus with drawing. So here I'm very conceptually in pseudocode saying draw character A in window 1 at coordinate x and y. Okay, anybody familiar with an API call? I think I've probably shown that to you earlier. That implements this abstract operation. In Java, everything is object-oriented. Everything is done on an object. So here I'm just saying the full call. So what object would this operation be invoked on in Java? Anybody? Sorry? Graphics. Okay. So target of draw in Java, on what kind of object is it invoked? There's a graphics object. Okay, there's a graphics object they came up with. Then they realized that the graphics object is not rich enough, and they came up with the graphics 2D object. And you have to cast they didn't change the API, so you have to take the graphics object you get and cast it to graphics 2D. It works, and you do all these operations. Okay. The word graphics, I believe, came from X Windows. X Windows had associated with it with each window something called a graphics context. Okay, so it was some state like what's your pen color, and is it dashed or not dashed, and that you set for that context you set, and then you went and made these draw calls. Okay, so on the graphics object you can set these things and then go and say fill over, draw string, draw oval, draw rectangle, and if your graphics pen is dashed, then everything will be drawn dashed, and if it's not dashed, it will be drawn correctly. Okay, so it's something associated with state. Okay, so there's a window, and there's the state on how to draw in the window, and that's what the graphics object is. Okay, and we see that here. We're saying graphics.draw oval with the obvious parameters, draw line, draw string, and all of these things are being done in this drawing here. Okay, so this is not challenging. Okay, it's 101 programming classes deal with this stuff. Here's the issue. So we've written this code to draw things. So these are really output calls, right? Where you would do print line, you're doing draw string. It's much nicer. You can draw on a particular part of the screen rather than append to some text window. Okay? And when do you do print line? Typically in response to some user input or when the application decides that the output has to change. Okay? So you could call it whenever new input is given or whenever that's whenever the, okay, so is there any other situation when you might want to call this code? So in teletype I/O, if the contents of the display visualization, which is just a bunch of lines, doesn't change, you don't call output code. In a Windows system, you may or may not call. Supposing my window is hidden behind some other window, and it's displaying the current weather, and the weather's just changed, and you say the temperature is now 75 degrees. The window is covered by some other window. Should that operation really be executed? There's something called lazy evaluation. Lazy evaluation says that don't do any evaluation unless the user can see its results. Okay? And so there's this classic example that there was a bunch of compilers, so people have contests among which is the fastest compiler. Okay? And one compiler looked at a piece of code and saw there was no output in it. So it didn't even compile the program. It said, there's no output, program will make no difference. So it was the fastest on that particular application. Okay? And you guys, you know that you'll work just before the deadline. Right? And it's got its advantages. It's got its disadvantages. If you didn't allocate enough time, you're in trouble. The advantage is that all the pain points somebody else has found, maybe I've changed the assignment, maybe I even canceled the assignment. And what was the point of doing the assignment early if I'm going to do all this stuff? So there is this lazy evaluation, and you can say, no, I want to only display it if it's going to be seen by the user. So that means I might go and execute this code 0 times if nobody sees it, or 1 time, or maybe n times also. So 0 and 1 we understand. 0 if this contents are not being seen. 1 if they're being seen. N times?
If the window is hidden, then we might not want to keep the image in memory, and when we want to redraw it, we're going to draw it back up.
Okay, that's a good point. So when I have drawn my circle, then the mail window came on top of it. User can't see it. Then the mail window got removed from it. At this point, 2 things got to happen. The operating system knows that the window got covered. It could, in backing store, go and store the contents and restore them later. Okay? And Nick, why did you say that was not a good idea?
Because graphics take up a lot of memory.
Graphics take up a lot of memory. And when you have windows with sub-windows in them, that means for each of these sub-windows, you've got to keep the contents. There may be lots of windows on your screen. Okay? So memory is one issue. Any other reason? systems have gone back and forth between this, whether they have backing stored or not. So the temperature was 70 degrees. I covered the window. Okay. 1 hour later, I uncovered the window and the temperature's dropped to 40. The backing store will show what value? Unless the backing store was written into by the application. Okay? It was not written into, it's the backing store. It will just store what was last viewed. It'll show you 70 degrees and you're going to freeze. Right? So, what if window is hidden? So the question then becomes, who repaints the window when it is exposed? Okay, window system or application? Original painting, we understand the application has to do. The question is repainting. Okay? And when the component is unexposed, the drawing might have changed, so system copy might not be current. So it's, in general, the application should redraw it. Okay? Which means not only is this code executed when input is given, but when output is required. And it could be required 0 times, 1 time, okay, or who knows how many times. Okay, so this is the key, because this is we're going away from sort of the underlying stream-based I/O to some other scheme. Okay, so there are these things called expose events, okay, or paint events. Expose event is from X. Okay, so I'm just thinking X terminology. And who knows that some window got exposed? It's the window manager. Okay, so there's a window system, there's a window manager. Window manager knows that which window is on top of another window. Knows the sort of tiling order. Okay, so when a window is resized, okay, then the exposed area has changed, right? When it's obscured, unobscured, okay, you get these events in the window client. And in general, the area of the window that gets exposed is not one nice rectangle, it's a bunch of rectangles. Okay? And at this point, the application can draw, and the window client, in Java, the window client just gets one rectangle that covers all the sub-rectangles. Okay? In X, you could get a list of all the sub-rectangles. Okay? And the window client can be lazy and can just draw the whole window. It says, I don't want to worry about this area and this area and this area. Or it can just draw only in the exposed areas. So that's what I'm saying here. So you can draw a complete window, or you can draw only the exposed areas. Okay. Now, if I draw the complete window, what happens to the drawings that are not exposed? What happens to the supposing I draw a circle in an area that is not exposed, that is being covered by the mail system, by the mail window? What will happen to that circle? Will it get? You don't ever see a circle appearing on a mail window, right? So what's going on underneath?
You can have the mail window again repaint on
So you have a little thing that it covers up. And if your system is slow, you would first see the circle being drawn and then the mail thing, right? The window system, because the window system also knows what the window manager events that the window manager sent to the window client. The stuff is going through the window system. The window system knows exactly what rectangles are exposed. So what could it do? It would clip everything that's not to be displayed. Okay? And that's why the lazy approach of drawing the whole rectangle area works. Okay? So window system clips in case app draws outside window bounds. Okay? And same thing with sub window. If in your text field you go and draw outside the text field, it's not as if it will be shown outside the text field. It will be only shown whatever you draw within a text field will be shown, not what's outside the text field. Okay? Okay, so application can request expose events and redraw. Okay, so we see this stuff here, that the exposed area is this rectangle right now. Okay, here's a more complicated situation with here's one exposed area, here's another exposed area, and of course the application might have drawn in the whole rectangle, but that stuff doesn't get displayed. Okay? And like I said, that the window system, the application may be only told about one rectangle. And when I looked at the Java API, it gave you one rectangle and not an array list or array of rectangles. Okay, so I assume Java just hides that away. And drawing outside exposed region will be clipped, like I said. And like I said, the window system could keep the last drawn pixels of each window as backing store. And we have a trade-off between time efficiency and space. We need more space, but we can just draw the image. We don't need to recompute it. And that's important. You know, you might compute a very complicated visualization. Anybody here doing graphics? Okay. So this is, okay, so if the windows are nested, then we have much more data, many more data structures to keep. And so we just have the application read. Okay? Okay, so this code must be called either when new output is, whenever new output is required, right? Or when new output is computed. So whenever the output logically changes, or whenever the output has to be redrawn. Okay, has to be redrawn. So how do we tell the system? You know, we write this code. How do we tell the system, please call this code when output is needed? How do we cooperate with the underlying system and tell it what to call?
We set a callback?
We provide a callback. Okay, we tell the system, here is some code that you should call whenever you need to call it. Okay, and you guys know the name of the callback method? Repaint. That's good. Now we're getting into some confusing issues. Repaint or paint. Repaint seems more correct, right? Because we're repainting it. But there's both repaint and paint in Java. And the question is, what's the difference? Okay, so called when what is to be drawn changes. Okay, so whenever last character or char x or char y on which this drawing depends changes, we want to call this code. Okay, and in that case, it's repaint that we call. Okay, and when exposed area changes, at that point it is the paint method. Okay, so how to accommodate both? So the question is, what is the Java API for receiving exposed? So you have a window client class. Okay, you have some window class. It's not quite a callback, and I'm going to spend some time complaining why it should have been a callback, but it's not a callback. So there's some JPanel in which you want to draw things, and you've got some code that actually draws the things. Okay, and the window manager is the one that knows, when the repainting should occur. Okay, so it goes and has a queue of paint events. At any one time, only one paint event is serviced. So a problem can occur that there are two threads that both want to repaint, and the question is, what are you going to get in the output if they get interleaved? So the system is making sure that only one event is processed at one time. So one event is processed, associated code is called, then the other event is processed, so the things get queued up, and that's how you serialize things. Okay? So whenever this window system, so the window manager goes and queues these events, the window manager goes and takes each event and says, let me go and invoke a specific method that will service this particular event. Okay? So window manager queues, window system empties the queue and calls some application code. Okay? What does it do? It doesn't know about the application code. It just says, I know about these sub-windows, like panels. They all have a method called paint. So I will call the paint method, passing it the graphics context. Remember, we are going to call our output, make our output calls on the graphics object. So we go and tell it, here's the context for your window. Okay? And this is done in a system class. So how does the window client class get involved? It says, okay, okay, so this guy can go and say, my output changed. So it can call repaint. So there's paint and repaint. What repaint does is queue up an event in the queue. So this queue that I talked about can contain events that are generated by the window manager, can also contain events generated by the application. So it goes and tells the window system, hey, I need things to be repainted. So put a paint event in there not because my screen just got exposed, but just because my screen contents have to be changed because my last character changed. My caret position changed. Okay? And what does repaint do? Repaint will call paint, and you in your window client class, if you don't want the paint method in the window class, you go and just override the paint method, and you can always call the class paint method. Okay, sorry, I went forward. So basically, you go and intercept the paint method by subclassing some window event. Okay, so this is what's happening here. That this thing is an extension of JFrame. JFrame has a paint method. Whenever a paint event is serviced, this particular paint method will be called by the window system. Since I have overridden the JFrame, it's my paint method that will be called. That can call the superclass paint method and then do some drawing. Okay? So when my exposed area changes, it will be called. Also, when I decide that my painting should be changed, because now I've got a new character, I'll call repaint. Repaint will go and put an event. That event will result in the paint method being called. So there's this level of indirection, and things get dropped. Okay? So that's what I'm saying. This is how you trigger the paint event. No argument. All you're saying is, please put a paint event, and the window system automatically finds your graphics context, gives it to you so that you can draw things. Okay? Questions? Okay. So we know how to draw things now. Let's go and look at how to get input. Okay? Input is a little bit more familiar. But hang on, it's not familiar. Let me go and show you how it was done at one time and how it still can be done. What we have to do is intercept not the paint event, but now some input events. So what I could do is I could go and have a window client class that subclasses the window class, and the window class knows when events are in our underlying operating system events will result in some methods being called here. That can result, those methods can be overridden. So the window class has a dispatch event in it. Okay? What you could do, so whenever an input event occurs, in fact, whenever any event occurs, a dispatch event method is called. And that dispatch event calls process event, okay, in that same class. Not in that class or some other class. So dispatch event just means, let's figure out which process event I should call in which object, in my window or in some windows. Okay? So a frames dispatch event can go and say, let me go and figure out which should I call this. Is this event relevant to a particular text field? In which case I'll call the process event in that text field. Or is it relevant for me? Okay? So there's process event and dispatch event. Okay? And what you could do, you could just go and override the process event or the dispatch event, actually, either of those things, to go and get input. Okay? And this was the approach used in Java 1.0, inheritance-based. Okay? You don't have a callback, you just go and override a method. We know that this method, both these methods will be called. This is on a fine-grained event, this is a more coarse-grained event. And if you want to do our own dispatching, we could override this. If you want to just do our own processing, we can override this. Okay, and we can then go and send the. Okay, and they got rid of this approach in 1.1. 1.1 and 1.0 were very different, and people said, oh, we finally figured out how to do object-oriented programming. And I shouldn't blame Java, the Java guys for 1.0. That was exactly the approach used in Smalltalk. And Java was, it was trying to create a language that was like Smalltalk, but in another context, and was focusing on portability. In fact, Gosling was creating a language for himself. He didn't even intend for it to be used today in a class like this, and people like me criticizing it later. Okay, and so this is exactly what Smalltalk did. And then now that a larger set of people were dealing with this, they found problems, and they said, and the problem they said was, what if my window client class needs to be a subclass of some other class? Because we don't have multiple inheritance, it's go and it has to be a subclass of this class, and so we have to duplicate code. Okay, and they said, oh, this is bad. This is was bad because a window client class is not a window class. It's a client class. Okay, it's a input processor. Okay, it's a text editor. It's not a text field. Okay, so they went to a delegation model. Okay, where the window client class is not a subclass of the window class. It has a reference to the subclass, and now it goes and says, here's a callback. Please go and invoke this method whenever something interesting happens. Okay? And there's two ways to do the callbacks. You could go and add yourself, and this is important from the point of view of shared window system. There's an object called toolkit. You can add yourself as a listener to all events on the toolkit. Okay? So you could add yourself as a listener, in which case every event is sent to you and to the appropriate window class. Okay? This is coarse-grained event tracking. That you can create every event in the system by going and adding yourself as a listener, not to a specific window, but to this. And then you could, of course, use this reference to go and look at the state of the text field or whatever you need. Okay, and that's something that's. But at this, if you do this, then you have to distinguish between whether it's a mouse event, whether it is a key event, whether it's on this text field or that text field. Okay, and so what happens is, but this is nice. There's a single way to get all events. Okay, and this is something I use in the telepointer implementation I'll give you. Okay, so I just want to show you what's going on underneath the covers a little bit to show what's happening. Okay, this is not what happens. What you do is you have a reference to the window class, and you add yourself as a mouse listener or a key listener or a mouse motion listener, and the process event in the window class goes and decides whether the event was a mouse event, a key event, or a mouse motion event, and calls the appropriate fine-grained method. Okay? So there's many ways to get events. There's the inheritance-based approach. There's the delegation-based approach. In the delegation-based approach, there is getting all the events, undiscriminated, or getting discriminated fine-grained events. Okay? So underneath what's happening is there's a dispatch event that results in a process event that results in these listeners being called. Okay? And if you ever go and override the process event and do something different, all the listeners will stop working. Okay? Because the listeners rely on this. Okay, so this is how we get. Okay. So you now have key pressed, mouse pressed, and these methods get called when the process event will either call the key pressed event or the mouse pressed event, depending on these two kinds of events. Okay. And this is exactly what you see here. Okay? This character drawer goes and adds itself as a mouse listener to itself, which means to all the events in JFrame. This is not a very nice implementation. Okay? You should really have a separate object. And now you get key typed or mouse pressed. And so as a mouse listener, you have to implement these methods. Okay? Okay, so this is something you guys this is not foreign from what adding an action listener. Action listener is a very specific kind of listener for a specific kind of widget. This is something you can do on any component. Okay? Action listener you can't do on a canvas, for instance. Okay? So we understand how at least the underlying system, Windows system is working. Okay. So I just want to point out the output processing uses inheritance. Okay, you override a method. And the input processing, which is not very good, and the input processing uses delegation. It is possible to use delegation even in output processing. Okay? You could go and have a paint listener and have a paint method. And this paint method could go and call the paint graphics method. Right? You don't have to make your window client class subclass of window. So this is something I did, for instance. There's something called delegate JPanel I have in my library, which you can add yourself as a listener to. And you don't have to go and subclass off this. You can just have a separate window class, client class, that either goes and uses a JPanel or a panel. It doesn't care. You just go and pass it the appropriate object, and it's not bound to one of these two classes. Okay? And I did this, but it's, I really still wish Java had done it right. In 1.1, they had done it right because, I can do this for every window class. Okay, I can have a delegate JPanel, I can have a delegate panel, I can have a delegate container. But then what happens is that my delegate container is not a delegate component. My container is a component, but my delegate container is a container, which is a component, but it's not a delegate component. Okay? So I lose my inheritance, the natural inheritance between delegate container and a delegate component. So you can do this, but it would have been much nicer if Swing had done it. But I believe SWT supports this. Okay? And when I go and give you my library, since I'm hiding things from you, there for the telepointer, you will be defining a paint listener. Okay, I'm using a specific kind of component here, so I don't have to worry about inheritance. So that's why I'm introducing paint listeners to you. That's exactly what you will implement, even though that's not quite Java. That's something you can build on top of Java, which I've done, but it's not quite Java. Okay, so my shareable library uses that. Okay, so we understand Java window system better now. Let's now go and try to answer all these questions. Now that we understand something about the system, let's try to figure out how to go and extend it to make a replicated window system. Okay? So how to create a telepointer? That seems like a really trivial problem, given what I've just told you. What are we doing? Drawing a little circle here. Okay? And we're going to figure out if the mouse is within the circle or not. If the mouse is within the circle and you drag it, you will repaint it at the new location. Not too hard. Okay. So what I can do is, so I've got a JFrame, and I can go and, to draw the circle in this, I would go and create a telepointer frame that's a subclass of JFrame that overrides the paint method. So I don't like this solution. Why not? There are two questions here. Does this work? And if it works, do you like it? Assume it works for now. Or you can answer either question. And what I'm hinting to you is that it won't work and I don't like it. I wouldn't have liked it even if it had worked.
Well, if we do this, is the telepointer now stuck in that specific frame?
Is it stuck in that frame? Yes. It is confined to that frame. So that's something, and you might want it to go from one frame to another frame.
And it means we can't subclass that frame another way if you want to.
You can't subclass that frame in another ways you want to. You can't even take an existing frame. You have to go into the application code, see all the frames it's creating, subclass them. Okay, so that defeats our purpose to some degree. Okay, having a telepointer that moves between frames, that will have to be implemented by just having, so that's something I don't quite solve for you. Okay, and that's something that I can't quite solve easily, I believe, using swing. Okay, okay, so that's why we don't like it. Cannot share existing user interfaces. Okay, and even if we have to go and subclass each frame, and if we subclass, then somebody else can't subclass it. And the idea here is that after the application programmer has written their program, we go there, we go and change each frame and to telepointer frame. And so there's no more programming to be done. But then, of course, the application programmer has to go back and change something. It's a mess. But suppose we didn't worry about that. Supposing we were creating not a generic system, but we were trying to create a telepointer in a specific application. Can you see why it might not work?
Is it possible that the telepointer is ping on the frame, but if you put other swing objects over it, it cannot sync?
If we put other swing objects over it, like what? So this is my particular user interface, and you're saying somehow this text area may be put on top of it?
Yeah, I don't know how swing draws these things.
Okay, so we don't quite know how swing draws things. We don't know the hierarchy. But there's a paint method in the frame. So here's the thing. The problem you're trying to indicate happens to occur because you have subcomponents. If you just had a frame and nothing inside it, it would work beautifully. Question is, what happens when you have subcomponents with their own paint methods, and now this area can be painted by my text area, and it can be painted by the frame. When an event occurs in this text area, the event is an event in this text area or an event in the frame?
It's initially an event in the frame, and then it's dispatched to the text area?
Or that could be it. Okay, that is initially an event in the frame, and it's dispatched to the text area. It's initially a paint in the text area, and it's dispatched to the children. Okay, and but ultimately, given this dispatching is done by Java components, right? There's a Java container that does all this work. So the question is, what did Java container decide to do? Did it decide to go and let the children override the parent, or the parent overrides the child?
The child overrides.
The child overrides the parent. Okay, so this is very interesting. When you think of overriding, we think of overriding that occurs because of the is-a relationship. There's also overriding that can occur because of the has-a relationship. And then the question is, are the attributes who wins? Okay, so so that's what I just said. A component can be painted by it and all of its ancestors and so forth. And like you said, smaller component, the child component, the child component overrides drawing and input processing of enclosing I don't know why I said static here. Okay, components. So what will happen to this telepointer? What will happen to this telepointer in the text area? The text area is going to be drawn on top of it. Right? So I can't, even if I don't mind doing this, cannot use nesting to draw a telepointer. The nesting scheme does not allow a telepointer on a frame.
Could we explicitly call the paint method of the text area if the text area is accessible to the telepointer frame?
So could we do some kind of manual dispatching ourselves? The trouble is we are some subclass of Java, and Java decides to do a certain way. And unless we go and override all the methods, we are stuck. Okay? And the main point is that the programmer who created this UI, they followed Java's rules. They were not following our rules. Indeed, if the programmer was cooperating, they could go in subclass container, could go and not call super.paint, it could call its own paint method, and which does the dispatching. and it could do all that stuff. But we want to be able to share user interfaces created by people who don't even know the user interfaces will be shared. Okay, and so this is summarizing discussion. We can replace the top-level frames window with one that draws movable telepointer shape. Cannot use nesting. Even if we could, cannot share existing user interfaces. So we are in trouble. Fortunately, Swing, not AWT, solves our problem by providing another abstraction. There's nesting and there's layering. Okay? And when you go and see a subcomponent, that is basically contained within the parent area. What you can also do is take an area and not subdivide it, but layer something else on top of it. Okay? And that's called a glass pane. One of the layering objects is a glass pane. Okay? And you can associate a frame. With the children components, you say add a child component to the frame. Now you don't go and add a child component. You go and set a glass pane, which has its own area, which also has a paint method, which also gets events. It's just like any other component, except it's not a child. It's layered on top. Okay? So it's layered. Okay? What does layering give you? The opposite of nesting. In nesting, the smaller component overrides a drawing and input processing of enclosed static. By static components, I mean children. Okay? That sort of, they're bound. Layering is a dynamic thing, and what layering does is it just grabs all the events, the paint method and all the events in the areas that it encompasses. Okay? So it's a larger area that is layered on top of some smaller areas. It just grabs the events. Okay? And the application programmer has created some static components, and we as collaboration guys can go and take all the frames, if you can discover all the frames, go and add layers to it to grab all the events. And then we can do what Nick was talking about. We can redispatch the events to the children. Okay, we grab them and then dispatch. Okay, that's a lot of work. And that's something I didn't want you guys to do, so I did it for you. And unfortunately, it's hard to do. And to do it correctly is a real pain. So it won't work completely. Anyway, so I want to go and show, I guess I'm trying to make the point here also that the overriding can be type or structure based. Okay, so hey, sometimes the bigger structure is winning, sometimes the smaller structure is winning, depending on nesting or layering. Okay, so I wanted to go and give you guys some abstraction that hides all this stuff from you, that will do the redispatching and so forth. Okay, so the question is, what should this abstraction be? Okay. And we have 5 minutes. Let's go and see how far we can get. Building algorithms, is hard, right? That's why you have all these algorithm classes. Building abstractions, I think, is even harder. Okay, and what do we see often? You want to do some task. You go and find some snippet of a code somewhere in Stack Overflow. You go and change it to make it work in your application. The fact is there was something common between your code and that code, right? Why couldn't that be an abstraction? And you just change some parameters and it works in your context. Okay, so it's not often. And that just shows you that how hard abstractions are to build. So let me just ask you, so let me just go through this exercise. This is a simple abstraction relatively. Supposing I'm willing to do all the redispatching. What API would you like from me? There's a bunch of frames in the application program. You want to go and attach a telepointer. You somehow discover these frames. You want to attach a telepointer to each frame. What API? What's the simplest API you can think of? You have a reference to each frame. Nick?
We encapsulate each frame in like a pointer class that's a reference to the frame.
Okay. So, okay.
Right, so I had it the other way around. I had the glass pane frame has a J-frame?
Actually, what am I doing here? Sorry, I'm just saying, sorry. I asked the question prematurely.
Okay.
This is just going and showing you what really happens. That a frame has a reference to a glass pane. Okay? And you can imagine a glass pane because it's layered on top. So that's how glass panes work. And this is all this stuff about redispatching that I just talked about. And like I said, my trick solution does not work in menus. Okay, and it's based on code found on the web. So now I'm going to ask you the question. This is what you had basically, some utility. It has a method called attach frame, and it can go and then set the telepointer in the frame. Okay, Swing wants the frame to have a telepointer, to have the glass pane, because it goes from the frame to determine what its layers are, and we can just have this facility, right? That's exactly what you were saying. So this is high level of abstraction. Whenever you add abstraction, you go and take some decisions away from the programmer. Have you lost in flexibility somewhat here? Is red the best color for the telepointer? Is oval the right shape for a telepointer? So what you might want to do is, have your cake and eat it too. You don't want to do the work, but you want to also not lose flexibility. So what do we want now? What API do we want now? Given that we know, the telepointer may be, well, actually, maybe red and an oval are the correct color. And I draw the right, wow, I didn't realize it. They match. I got the right size. What might we want to do now? What API, how might the API be different now?
We want to be able to set the attributes of the pointer through the utility class.
Some attributes, or we may just want to draw it. Drawing a pointer is not so hard, right? So we can just draw our own shape, in which case we might want to just write a little painting class saying, give me a graphics object and I'll draw the telepointer on it and you do everything else. You figure out whether the mouse is being dragged within the circle or not, okay? And so I have this object as an extendable telepointer glass pane, okay? And it takes in its constructor the frame that it's associated with, right? So that's how this attach frame thing is. It's bound to a particular frame, and it has an add painter method that takes a graphics painter as an argument, and the graphics painter is expected to have a paint method in it. Okay, not too hard. Okay, and what this guy can, the graphics painter is also can get a reference to this guy, and it can get the position of the x and y, the pointer, to know, because it has to know where to draw. It also has to, and we can also allow these attributes that Nick was talking about, that we can have a glass pane controller that has the width and the height that could be customizable now beyond not. So we've decided how to paint it, and some other programmer might decide how big the telepointer might be. Okay. And so there's a graphics painter interface that is not a Java interface, because Java does not allow delegation in painting. It's something that I created. Here's my extendable glass pointer plane. I go and pass it the telepointed frame. Okay, and then I go and say add painter to this telepointer thing. And here's my glass pane controller. It says, what should be the width, height, and should I show the telepointer or not? Okay, we can imagine that the painting method will only show the telepointer if the control says yes. Okay, so these are things that you might want to customize. In fact, in your next assignment, you will be customizing these features. So you'll be using this facility. Okay, so we know at least how to draw a telepointer. Okay, and what I'll do is, so the painter should choose the dimensions and controller to draw shape. And so the basic algorithm is instantiate a telepointer glass pane, passing it a JFrame, implement a telepointer painter. Painter should reference the telepointer glass pane to get the paint position, pointer position, and should reference the controller to get the paint dimensions. Okay. So what I'll do today is put on the web the whole assignment. It is divided into 3 parts. The first part just says, take your frames and put a pointer on top. Forget how to share it. That part you can do today, okay? After what I've told you. And the next part is make it shareable. That you will need Wednesday's lecture for. And then I'm going to also give you extra credit that says filter out the spurious draglines. Okay? So I think we've left it at the right point. Okay, great. Okay, so last time we looked at the general concept of replicated shared windows, how the algorithm is supposed to work. And now the question is, how do we implement it in a real system? Okay, and we're taking Java as an example. We saw how to create a telepointer last time. That was enough for you to start on the first part of your next assignment. And we're going to now look at the remaining issues. Okay, so let's go and look at how to intercept input for broadcast and how to inject. So you've got to intercept input at one end, and you've got to then inject it at the other end. So how to do the interception and the injection. So the way I told you it would work is that there is a channel of communication between the Windows system and the application. And you would just intercept in the channel. Somehow you would put a probe in there. If this was a network, there would be no problems. Okay? In Java, it's not the network. But like I said, if it's a network, you just put a proxy in there. And the question is that given that it's not a network, how to tap and inject input in Java. I told you a solution that could work. I told you that there is something called a toolkit class. In the toolkit class, you can add an AWT listener, and every event that the toolkit, it's really a Windows system. It's Windows system plus toolkit. Every event that the toolkit knows about, it'll go and tell a listener about. Okay, so that's how we can intercept input. How do we inject input? Well, that becomes trickier. Okay, this is a listener, and you can call the event dispatch method is called, and the event dispatch method is also called on the regular on anybody else who's a listener. Okay. So you can intercept events, and this is not really a proxy. Okay, it's not as if you're blocking events from going into the regular application. Okay, you're just adding a listener, which may not be bad. Okay, but just to tell you a difference. And there's no direct way to inject or stop events. And what you can do is look at the event, look at what components fire that event, figure out which the deepest component is that should get the event and dispatch it. So you've got to do a lot of work. Actually, a nicer solution that Java has, which is more conducive to putting a proxy. All events go to an application through an event queue. Basically, they get queued up in an event queue. Okay? Somebody goes and puts something in that event queue. And what Java lets you do is replace the system event queue with your own event queue. And that event queue can decide whether to dispatch the event to the application or not. So this is great. When I discovered this, I was first going through the previous solution. Discovered this, I said, this is perfect. And here's the API. You can just say toolkit, get default toolkit, which is the toolkit object I talked about earlier, get system event queue, and make my event queue the real event queue and push the other ones behind. If I pop mine, then the other guys become the event. Okay, so this is a very powerful facility in Java. Okay. And but you must, in this case, still remember to forward the events to the application. Okay, and so there's that problem, and you must prevent cycles. So you must make sure that So since you have your own event queue, you can intercept events, and then you can, in a remote place, inject events. Okay, you're all in control. But you've got to make sure that you have to prevent cycles. You have to forward it to the application. Must filter uncoupled events. Okay, all these events that you don't want to know about. You want to just know about the real I/O events. You don't want to know about window moves and maybe paint events. Okay, those you don't want to send across the network. So there's a lot of work you have to do if you want to implement your own queue. Okay, to make your life easy, and so that you can just focus on the distribution aspects. Okay, I've got an object that is an injectable, interceptable queue. Okay, and it's designed to be collaborative, to allow collaboration. And what I've essentially done is, when you go and instantiate this object, it goes and makes itself the system event queue. Okay? And what you can now do is listen to events from it. Okay? And this is what you have to write. And the events go to you. And only the events that make sense at the remote end, the ones we're going to send, okay, as per my assignment specification, let's say. And this is where there may be a problem. Okay? The reason why things may not work could be because Java is not doing the things properly, or I'm not sending you all the events. Okay, but I spent a lot of time trying to figure out which events don't make, I can safely not send across. Okay, because between events there's state, so some events must follow previous events, and if I go and send an event for which the predecessor has not been sent, the other end may get confused. Okay, so I played around a lot. And if you go and look at the code, I have a little data structure that says what kind of events go across, what don't, and you can always subclass my class to go and send the events you want to send. But this is an API that you also need to know. Okay. So what you do is you define a listener to get the filtered events. You only get filtered events, and some certain events are not sent across. And here's the method you call to add yourself as a listener, and you have to somehow get access to this particular event queue. Okay, how many such event queues will exist in the system in a VM? One, you want to get all the events. Okay, so this is a singleton class, and which means you can invoke a static method on this class to get an instance of this class. Okay, this is a trick that's used a lot. Okay, this is really a class that generates another object is called a factory often, and you make the same class a factory. Okay, so you get the event queue from there, and then you can add yourself as a listener to that. Okay, so not too hard. So how do you inject an event? Well, there's a method called dispatch received event. So this queue knows that it could be talking to other queues across the network. And there's a dispatch event in this queue that it inherits. An extendable event queue also inherits dispatch event, a dispatch event method. If you go and call that method, it goes to the regular listeners. Okay, and which this guy does. Okay, it does forward the events. The events it gets, it sends it to it does super.dispatch. Okay, and if you do dispatch received events, that will call a separate method from dispatch event. So dispatch event is the method that's called from the toolkit. Okay, to say here's an event, and this guy goes and says, okay, I'll send it across to the net. I'll filter the event, and I'll send the filtered events to some remote to the listeners. Plus, I'll do super.dispatch. Okay. If you do dispatch received event, it just does super.dispatch. It does not go and send it to the listeners. Okay, so you avoid cycles. Okay, so you have two different methods, and does not fire a new event if you do dispatch received event. Okay, and you have to convert somehow a network event to a local event. Okay, and to convert the network event to the local event, I have a utility, and that is the communication event support. And communication event support is an object we'll see later. You can get that communication event support from the queue and ask it to convert a remote event into a local event. Okay, so that's something else you have to do. that you have to send a serializable event, an event that has a network representation, and convert it back into a local event. And this is a facility that provides that. Okay, so we'll convert serializable event to local event. Okay, so that's the API. The general concept is that I'll save you guys from doing certain tasks. Okay, save you from figuring out cycles and save you from filtering out events. Okay, and here's the interface of that event queue. You can add yourself as a handler, you can remove yourself as a handler, you can clear event handlers. And these two methods are the ones that are different. That this is the one that will do super.dispatch, plus it will go and send the event to the listeners. This one will just do super.dispatch. It will not send the event to the listeners. Okay? And we saw in our IAM application, there was replicated add and observable add. And that's, one of the replicated add sent the add across the network, and the observable add did not. So that's the same difference. Okay? So now you know how to create a telepointer, how to intercept input, how to inject received. Okay? So you're getting near what you need to do to implement your assignment. Okay, questions so far? Okay, how to translate window IDs. So how to find corresponding windows in different replicas, and we guys saw some solutions earlier when we were looking at replicated model systems. How were we going to take two models generically, or two objects generically, and find the correspondence among them? Anybody remember? You want to think again? Use the object type. So if I know there's only one instance of a frame, then I know the frame here corresponds to that frame. If I know there's exactly one text field, then the text field here corresponds to that text field. But with a frame, maybe. For text field, definitely not. So how are we going to know that these are corresponding? Very good. We said that, look, maybe these guys will be instantiated in the same order. Okay? And in the case of Windows, we also have names. So in the assignment, I give you guys flexibility. I myself used order because this way I don't have to rely on the application having given each window or widget a name. Okay? Because there's no inherent name. It's just you have to do set name. Okay? The window 2 and window 1 correspond to each other, and we have to go and send some intermediate window ID, and we have to know that these two guys correspond. So can assume same sequence of windows, okay, and can use names of Java windows. Okay. So these are two alternatives. So then the question becomes how to replace local window IDs in events with global IDs, okay, and global IDs in events with local IDs. So somehow you've got a data structure that will associate a local ID with a global ID, and then you have to go and replace them, okay. So it's kind of the obvious thing here. Maybe just get the algorithm. Given some AWT event E, whose source is some component C, okay, what does replacement mean? We send a serializable AWT event, okay, and that's a data structure I also give you. So you don't have to know about how to make something serializable. You've done that in your previous project. You send the same event E, plus you go and send an ID that this component C corresponds to, okay, and you've got some data structure to go and do that. So I've got for you a class that takes in its constructor the AWT event and some string. Okay, if you're using the order of instantiation, then these are numbers. You can always convert a number to a string and a string back to a number. But in case you want to make it a name, string allows that to happen. Okay, so you have this, and then given a serializable event S, event E, okay, and ID I, again, at least I'm consistent. What I do is I go and call some method that will convert that to a dispatched event, okay? So that will go and take E and the source, and we will dispatch this particular event to extendable event queue, okay? The extendable event queue expects some local event, okay? You got a serializable event. So what you do is you go and call some magic routine, which I'll just talk about, which takes the event E, which you got, and the ID, the global ID, and the local component. And to get the local component, you just call some function to component that you've defined that takes the global ID, finds the local guy, and then goes and says, join these two things together and create a dispatched event. And that's the one you send to extendable event queue. Okay? And there is this communication AWT event support I just talked about earlier. That's the one that returns an AWT event to you and takes as arguments the serializable event and the component. Okay? So you just have to go and do the local translation. So your work is just doing conceptually what you have to do. Convert this into a global ID, convert the back into a local ID, and how to go and go from the event to the serializable event to the local dispatch event, you don't have to worry about. Okay? There's probably some details that are messy here, and that's the reason I've given you this code. Okay, questions? And like I said before, to get the communication events, AWT event support, you just find the singleton event queue, get the support, and ask it to convert. Okay. So here's what's happening. Here you've taken a local event, converted that into a serializable event. Okay. Here you've got a serializable event, and you find the dispatched event, and you take the dispatched event and dispatch it to the queue, and the dispatched event you get from a code like this. Okay. So I'm just showing you some snippet. You can't go and search the stuff in Stack Overflow because there's not enough experience with this code. So just to make everything clear. Okay. And the two component is written by programmer to translate between global ID and local component. Okay. So we still have to figure out how to find these corresponding events. We know that we have a data structure, and now we have to find maybe find the names of the windows, maybe find the instantiation order. So how do you find the instantiation order? How do you know when a window got instantiated? You didn't write that program. You're taking somebody else's program and sharing it. So you need some way to figure out that this window got instantiated. Either to extract its name. Okay, what you're going to do is you're going to build a little table, simple table, that associates components with IDs and IDs with components, right? So you have to somehow populate the table and look up the table. To do that, you have to know a window got created. So when the window got created, you can extract its name and put the data structure in. Or you can, and if you're looking at window instantiation, you have to know this is the nth window instantiated. So somehow you have to find out that a window got instantiated. Okay. And you can, of course, go and change the program application. You don't want to do that. So once we can find a window, we can, I should change the spelling at some point, recursively find all of its descendants, okay, and register them. So supposing a frame got instantiated, I can go and register all of its components in some order, okay, pre-order, post-order, whatever. And then when I find that, then at the other end also, it's going to use the same algorithm. So given a parent structure, once I know when it is instantiated, I can go and in a certain order instantiate all its children. Okay, same order can be used at the other end, so we know that they'll correspond. Okay? But then I have to know that this particular frame got instantiated, and now this frame got instantiated. I need to somehow find that information. Okay? And this is what this tells you how to go and find the children of a component. Again, you can easily look this up, but there's a get components method which tells you the children, and from that you can get their children, and you can get all the descendants. Okay? So how do we know a window got instantiated? We just need to be somehow told. Okay? And in Java, there's a resize event that gets sent. The first time a window is created, a resize event gets sent. Not a window creation event, but a resize event. And I think that it was the same case in X also. Okay? So we just listen to resize events. We have to listen to them anyway. Okay? Because when the window gets resized here, it must get resized there also. Okay? So my queue is sending you resize events. Your listener goes and says, I got a resize event. Okay? Let me go and register the event. Okay? So that's something else you have to do. And how do you know that the event is resized? Well, you can look up the API, or I've given you a little library routine that says, given an event, is that resized? Call that, and you know it's a resize event. Okay? So again, some detail. The main point here is that somehow you need to know not only the traffic, that's the input-output traffic, but you also need to know about window creation. Okay? If you're going to correspond with windows. Okay? So if E is window creation, which is resize event, then register the global IDs of its subtree if the subtree has not already been registered. Okay, so you've got to go and have somewhere logic like this. You might just get two resize events, and you can be smarter and say, have I seen this resize event before? Which is equivalent of saying, have I registered this window and its subcomponents before? Okay, so if I registered the parent, then I must have registered its children also. And it's not guaranteed that, and I actually forget that you will get the because a frame also, a window, will have its children added incrementally. And you might get the resize event for the parent first, and then you might get resize events for the children underneath. So I forget what the exact order is. So just be ready to receive resize events for every component. Okay? And when you see one for a component, just go ahead and register all of its children also. And if the children send events later, well, they're already registered. Okay? Questions? Okay, so now there becomes a little issue. Resize event is sent both when the window is resized and it is created. Okay? And you want to do two different things under these two conditions. Okay? You want to dispatch normal received resize events, okay, so that the resize occurs at the other end. And these funny resize events, which are window creation events, you want to go and actually register the subtree. Okay? You don't want to pass it to the other end. Okay, if you pass it to the other end, who knows what, you might do something, you might go and register something different. It might not even work. I don't know. So you should not send the resize events that are window creation events. You should only send resize events that are true resize events. So how could you discriminate between these two kinds of situations? Or how could you avoid sending the first resize event? There's many ways possible. Firstly, you have to get those resize events too. Okay? So you have to attach your listeners at the right point. Okay, and then you have to go and discriminate among these. So keep some data structure basically. Okay? And you want to, and here's an important thing. You want to connect your queue listener before window tree created to get resize events. Okay, so somewhere in your application, it's going to create a window tree. Okay, before that code is executed, you want to go to the event queue and say, I want to listen for events. Because if you do it after, so this is something that's that may, this is a mistake you might make, that you might go and run your application, then go and add these queues. Okay, so just make sure that your this listener is added before that. Okay, and now you want to make sure that these resize events are not broadcast, or even if they're broadcast, they are not acted on at the other end. Okay, and there are really three solutions I came up with. So you can always attach your broadcaster after the window tree is created. Okay, that means you have to have one listener to get your resize events and one listener to broadcast events. Okay, if you don't want to create two different objects, you could have a little special mode in the broadcaster that says, I'm now in the, the application has been created, so now I will forward the events, and before that I'll just go and create my windows. Okay, and the other thing is to be very lazy at the sending and send all the events across. And your receive listener, okay, at some point you will ask the distribution library to go and make some object of yours a receive listener. That can be done after the application windows have been created. Okay, so that you don't recreate, you don't go and use those events to go and change your registry. Okay, so there's many solutions possible, and I'll let you guys choose among them. But I do want to point out this, okay, that there's really two different kinds of resize events. Okay, you want different actions. Okay, so we've got, the concept we've got, and now we are looking at the details. So it's really, this is really for the assignment. There's not much I can say about this except give you the facts. So how to filter events. So there's some window manager events that you want to filter by type, and that's done by the library. Okay, so this you don't have to worry about. Those events are getting filtered out. But if you want to filter your mouse drags, okay, you want to go and filter. You want to firstly know it's a mouse drag. Secondly, you want to know at what time that event came. Okay, and you can always Google, or you can just go and use this code. You can always find the current time. Okay, and you can take an event and say, is it mouse dragged? Okay, and you'll get, and this is a library I've provided, and it'll tell you it's a mouse drag event. Okay, so you can do that now. And again, I want to say that you want to ensure that the last mouse drag is seen. Okay. Filter by top window name. Okay, so you want to, you'll be in your assignment, you'll be saying, I'll be telling you, okay, don't send events for the locking window. Okay, and somehow you have to know it's a locking window. Okay, we're going to use names of windows to figure out whether they are locking windows or not. So you have to somehow know that this event occurred in some component of a locking window. And if it occurred in some component of a locking window, I will not send them event across. Okay. So how do you figure out whether which component of an event occurred in? You can always do get source to figure out what the deepest component is. Okay, that'll return to you an object. Not all events occur on components. Okay, then you have to figure out whether it's a component or not, and then from that you have to go to the topmost window, because that's the one we will use to filter. And you can always recursively go up, okay, by going to parent, but you can just use this particular piece of code that says get me the root of the component, and you've got the name. Okay, so need to cast source as component. So these are some details you need to know to do your filtering. Okay, so again, there's no API, there's no document. This is the API. So this is the recording, or this is the slides you need to look at for your assignment to get the details. Okay, and it's pretty strict. It's a very simple API. It's hardly any code. And this is actually not my API. This is the API that I have searched for. So this is Okay, now let's get into some conceptual things. So we're done with replicated systems. Okay, we're done with the assignment. You don't need any more for this. But this is to look back at Windows systems and see whether there's another way, other algorithms we can use, other architectures we can use. So when I was talking about shared Windows systems, I said, how could you do shared Windows systems? And I think Nick said we can do centralized. Okay, and we can do replicated, as I've shown. Okay, replicated means that every computer is running the applications. Okay, and that really means that every computer has those applications. Okay, so if you've got a PowerPoint on one computer, you need a PowerPoint on the other computer also. It's not as if you can just share a PowerPoint from one computer. Okay? So let's go and look at a centralized system now. So what's going to happen? We're still going to have multiple collaboration-aware window systems, collaboration-unaware window systems underneath. Okay. We're going to have only one of these applications, and we are still going to have some kind of proxy we saw last time at each system, so that there can be distributed interaction. Okay, because if this is unaware, something here must be aware, and that's our proxy stuff. Okay, so the question now is, what's this intermediate? What's a protocol of communication between these guys when we have centralized systems? Okay, so let's say the user says press A, and the application is going to get, okay, so what happens with press A? That corresponds to this particular event. And let's say this is my master computer. That's where the application resides. And this is slave. When I get this particular event at the input distributor, what should it do? Right?
Forward the event to the master.
Forward. Right now it's broadcasting. It's sending it to all the input distributors. Now it's a relayer. Okay? So that goes and sends it to this guy after translation. Now this guy goes and makes a draw method call on its input distributor. What should this proxy do with this call? So this guy says draw a line to its window system. What do you want to happen now at the remote ends? Draw a line. And how would you ensure that?
We might have to intercept the commands from draw a line and have those be forwarded.
Okay, so now they'll be broadcast.
Broadcast.
Okay, so in the replicated architecture, we took the events, we broadcast them. Now we unicast the input event, okay, to the master, and we broadcast the output to all the slaves. So where there was input broadcast, now there is output broadcast, which means you have to somehow intercept the output, okay, which is going to be a real issue in Java. Okay, you have to intercept input in both cases. In one case you broadcast the input, in one case you relay the input. But the output has to be broadcast. Okay. So here's your architecture now. We have our master computer, which runs the collaboration unaware application. We have the slave computers, which just have the window systems and the proxies. Okay, they are not input distributors now. I'm just calling them proxies. And the shared application runs on the master computer of only one of the collaborators. Okay, and the shared application runs, just in case you didn't get the message. And each user's input is relayed to application through proxies. Okay, so the master gets the sum total of master gets events from multiple sources. In the replicated architecture, each replica got input only from one user. Now this one is getting input from multiple users. Okay, and each output of application broadcast to all users through proxies. Okay, that's the basic idea. And we can just go through this in more detail. You press A, the event A gets sent to the I/O. Now I'm calling it an I/O relayer. Okay, it's not broadcasting. All it's doing is getting output from the master and giving output to the master. Okay, it's just a relayer, and it translates it to a global ID. Okay, so this translation thing you're doing in your assignment is not just confined to replicated systems. The window application thinks that it got the input from window W1, and so slave relayer proxy relays input. It makes a draw call, The draw call is sent to the local window system, and it's sent to the remote window systems, which go in forward. Okay, so that's your algorithm. Well, that's your, at least your architecture, and proxies translate window IDs as before. Okay, so let's look at our algorithm in more detail. So this is a replicated algorithm, and let's see whether how this will change in the centralized case. So do we still create a telepointer window at each site? Yeah?
Yes.
Okay. You still need a telepointer. Okay. And the telepointer could be, each guy could have its so should we just create this at the, this is interesting. I didn't think of it before I asked you this question. So do we need that to happen at each site or only at the master?
If all of the draw events are going to be forwarded to each of the slaves, then well, we could take that to the extreme and say you don't have to do anything in the slaves, and the master just like sends a bitmap image of what the window looks like, which is not feasible. Which is not something you want to be doing, but is the extreme end of the master can do absolutely everything.
Yeah, and the master, we're already forwarding the draw calls from the master client. We now, as collaboration, we have added telepointer, right? We have written some code. We could recursively share our code in a centralized way and make sure the telepointer is displayed at all ends. We could do that. And it'll work because there is some draw call being made by our code to draw the telepointer. We could forward that. And similarly, whenever the telepointer changes, we could forward the events there. But I wasn't thinking of that. We could do it. There's all kinds of problems with centralized systems. And there are all kinds of problems with replicated systems also. As it turns out in the case of, and we'll see this later. Okay, this is a good question to think about. As it turns out, when we look at the pros and cons, replicating the telepointer is going to have all the pros of replicated systems and none of the cons of replicated systems. Okay? So we might as well replicate the telepointer and have code running on each computer so that now our slave is more than a slave. It's also managing telepointers. And then we can also have multiple telepointers, one for each user, which is a good thing. That will be a hybrid architecture. It won't be a pure architecture centralized. But that is what I was thinking of. And the intellectual argument is that that's the right balance. Okay? So we'll look at the pros and cons in great depth of replicated and centralized systems and think about it later. And I believe that telepointers will have all the pros of replicated systems and none of the cons. Okay? So we'll still create in each window a telepointer. Okay? So for each window, including telepointer input I should be followed by matching window event dispatched. Okay? So at the master, so what this is saying is that go and give the event to my local application, my local, do whatever you want to do with the event, whatever you can do locally with the event. Okay? That's what this is saying. So in the replicated architecture, it means it goes to the replicated application. So now, clearly, we want to do this at the master end, right? We want to go and dispatch it to our application. At the slave, do we want to dispatch it, do some normal processing, local processing with the event? We're going to forward it to the master. But should we also do super.dispatch in the event queue?
No, because there's nothing to dispatch it to.
No, because nothing to dispatch. That's sort of that seems like the obvious answer, right? Well, not so obvious, only one person answered that. Other people couldn't even think about the answer. What if the event is a window move? One of these uncoupled events. So there are certain actions the window system takes underneath. Or what if it's a telepointer move, in which case you want to go and forward it to the local guy and also send the telepointer move to the other end. Okay? So they might, if we do super.dispatch and there are no listeners, nothing happens. Just in case there are some local listeners, like a telepointer listener, let's go and forward the event. Okay? And certain events will be processed by the underlying window system, by some higher level layers like window moves. Okay? So we'll go and let those be processed so that when my window moves on my computer, some action occurs, which doesn't occur at the remote end. Okay? So we'll go and dispatch it, the next argument that really, for most events, the application events, there's nothing dispatched. Okay? And now, for each replica of transmit I, then I should be followed by matching Windows event sent. Now we just say for the master, if transmit I, okay, and if coupled I. If the event is not coupled event, then we don't go and send it across. Okay, which is what this transmit I is about. Sorry. So again, we go and send it to the master and not to to everybody. And now when we receive an event, there's two cases. Are we slaves? Are we the master? So if we are the master, when we receive an event, we should go and dispatch it to the master application, right? And what do we do then? We should then we go and I guess this falls down. I can't really show one-to-one correspondence. Let's just go to the next slide and see the various cases. So master and slave, for each window W, create telepointer WT, and for each window, including telepointer event I, okay, I should be followed by matching window event dispatched, okay. Just for instance, if it's telepointer, we want to dispatch it. If it's a move window, we want to dispatch it so that it's moved. And if it's slave and transmit I, then I should be followed by matching window event sent to master. If it is a master and he receives an event, nothing. Right? And now we look at the two cases, which was getting difficult to see there. Master receiver, for each window event received R, it should be followed by matching event dispatched. And now for each output call O, it should be followed by a broadcast.
So in this, does each slave still replicate the window structure and all the sub-windows?
Yes. Okay, so that's that because you have a physical window here. So you have to create a physical window on your system.
All right, but I was thinking like the slave could just have like a single frame, and if we take every draw call that would be generated in the master and forward it, then we could maybe do this without having the window structure. The window structure is a model and state that that can be centralized.
Okay. So did you? So what? Let me just say what Nick was saying. That he's saying that look, we still need the top level window at each site. Okay, but a top level window has sub windows like text fields and so forth. So why don't we create at the slave only the top level window, and let the structure be created at the master only? Okay, and in fact, okay. So let me now.
I mean, it seems to me like the more literate you are about what you're sending around, the more data you don't have to send. Whereas, like, if you start sending every draw call, you're getting really close to sending every pixel, which you could probably do better with just using image compression than dealing with all the overhead around the sender.
So you're saying that look, we have to worry about performance, and we don't want to send every draw call across the network. And you're saying draw calls can draw pixels also. Now, in the algorithm I gave you, every draw call is sent. Okay, So there are two different, and so, but you guys are talking of pixels also, but I'm talking of draw line and draw character. And you're saying, well, if you're sending draw images, then we can compress things, and we can say, I've already sent this thing before, so let me go and just send the difference between the old screen contents and the new screen contents in the next call. Okay, so there's many things going on here. Okay, so did you see how so how is the window structure related to draw calls? When I say draw, what arguments was the draw taking from the last few slides? Do you guys remember? Coordinates and draw line at this place in this window. Okay. In Java, think about it. When your paint method is called in a particular component, and the component has a graphics object. And when you say draw, it's drawing relative to that particular component. Okay. My draw call was Java independent, so it says that basically a draw call needs a window as an argument. Okay. So the question now is that if my application went and invoked a draw on a sub window, okay, and the other end doesn't have a sub window, then what would I have to do? I would have to convert that draw call into some draw pixels call in the top level window, which is why you guys were sort of combining the pixel idea and send the draw pixels. Okay. Sometimes you have to do that. Okay. That has the obvious problem that you're sending a lot of pixels rather than saying just the coordinates of the line. That problem can be alleviated by sending diffs, but it's much better to just go and send the draw line across as long as you have the window structure at the other end. Okay? Rather than finding indirectly what changed through this diffs, just go directly and say draw at the other end and just create the window structure remotely. You want to replicate as much information as possible at the other end, as long as the replication doesn't cause any problems. And if we don't see any problems in creating a window structure at the other end, replicate it. Okay. Happy with that argument? Okay, slave receiver. For each window request received, it should go and do a request made. Okay. So the master is doing a request sent to everybody, and this is just going and request. It's actually doing the draw on the subnet. Okay. So you can see this is more complicated than the replicated algorithm. This is what I can ask you in the exam, but I'm not asking you in the actual assignment. Okay. So let's look at some pros and cons of choosing the centralized versus replicated. Okay, this is one of those big issues. Okay. And this is similar to centralized versus replicated shared model systems. And do you guys remember replicated versus centralized model systems, the pros and cons? The pros of replicated systems are? Nick?
Generally, I think that we discussed there were a lot of pros for centralized systems. Enough that I'm actually kind of drawing a blank, trying to come up with good rationale for using a replicated model system.
Okay, so there's a local application running on your computer.
But that probably needs to have performance boost.
Performance, right? So when you guys have Dropbox, you can, or when you use Google Drive, you've got the file locally. When you go to the web to go and get the web file and download it, you're paying the download cost, right? So there's the local format. And okay, so what are the pros of centralized systems? What are the cons of replicated systems? We saw a lot of those. Sorry? Consistency. And certain kinds of operations you can not handle.
Operations with side effects.
With side effects.
That data don't fare well.
Okay, so operations with side effects, non-deterministic operations, the random number example. So consistency issues of causality and concurrent operations. Okay, correctness of performance issues when model is non-deterministic, accesses central resources, and has side effects. Okay, all those problems occur with centralized replicated model systems. Do they still occur with replicated shared window systems?
Yes.
Everything is replicated. Even more stuff is replicated. Think of your model interactor approach. In your replicated system, the model was replicated and the interactor. Well, it was so the complete replica runs in both cases. Okay, so you have all these problems, and it's just that the sharing is done at a lower level, but the application is replicated. Okay, and for example, if the application draws a random number, it's still going to have the same problem is going to occur. Okay, it's just that the sharing is provided at the lower layer. The application is still completely replicated. And one of the solutions we saw was that we could have a distinguished model or a centralized model that did all these nasty things. Forget consistency, that we deal with later, but at least the non-determinism, the side effects issues we could solve this way. The problem with shared window systems is that they really, really expect the application to be collaboration unaware. Okay, this means that the application knows that it's a master, it's running at a distinguished location or not. Okay, so this problem, you can't use this application-specific solution if supporting collaboration unaware applications, and that's the goal of shared window systems, to take existing applications and share them. Okay, so to some degree the problem got worse. Okay, that's one of my points here, that shared window systems in comparison to shared model systems, they give you WYSIWIS coupling or more or less WYSIWIS coupling, but they create many more headaches. They also give you collaboration unaware applications, but they create headaches. Okay, now let's go and look at the centralized systems. Okay, feedback times involve round-trip delays in the case of centralized model systems. Do we still have delays? Same problem. We solved some of the problems with querying. Okay, when you query for data, say you're going to scroll some window, okay, or you're going to refresh a window and say, give me the latest update. That stuff could be done locally in the case of centralized model systems, okay, because we did caching. What about in centralized window systems? When I scroll, can I be confined to just local communication? When I refresh and I say, please go and call your paint method again, can there be just local processing done? Where's the paint method executing? Master. Where's the scrolling code being executed? In the toolkit, in the master. The toolkit is centralized. So there's far more stuff that's centralized. Now, in this picture, only the model was centralized. Now the interactor and the toolkit are centralized, and the only part that's not centralized, that's replicated, is the window system with its tree. And if Nick had its way, even the window tree wouldn't be replicated, and only the top level window would be. Okay? So you're going to have, the high level state cannot be cached because the underlying code is not there to process the high level state. Okay? So it's far slower. I mean, if you ever use remote desktop, it's slow. If you use Google Docs, which are centralized model systems, they are not slow because a lot of the processing is happening in the browser. You scroll, it's only happening in the browser. It's only when you go and insert some text that it goes to the server, and even there it's doing a replicated algorithm actually. Okay, so where it's not waiting for you for consistency before giving you feedback. So I told you the replicated situation got worse. The centralized situation also got worse. Okay. So problems of centralization and replication get aggravated. So collaboration awareness required for distinguished process in replicated systems, which you can't have. In central system, round-trip delay for readable model state. Okay. Plus other problems. Okay. So we're not done. There's a whole lot of other problems that arise in centralized systems. Okay. And by the way, that non-determinism problem and side effects and all those problems, they're a killer. You guys are building a replicated Windows system. No commercial Windows system today is replicated. Okay? So all these problems I'm talking about, I'm going to go through. Most of these problems that occur in centralized case. And we're going to see how to address those. And some of these extra problems occur also in replicated systems. But these are real problems. Okay? Okay, one of the problems of consistency we saw was, I can type A, and I'm going to type Apple maybe. So A got to the window application. And before I can type Apple, you want to type Bob. And your B got mixed with my A. Okay? That happens in shared model systems. That happens in shared window systems. Okay? We need some kind of concurrency control to solve this problem. And that's what's going to happen in your next assignment after next one. Okay? But this problem we can't solve. Okay, these things got interleaved. And this is where you need transactions, basically. Okay? So user input can get undesirably mixed. Yeah?
So did we discuss how to actually intercept the draw calls?
No. So we're going to look at that later.
Okay.
Assuming we can do that magically.
All right.
Let's go and see what the pros and cons are. So that's going to be a little bit of a detail. And I saw how you guys were a little passive doing the details because, there's not much thinking involved. So we're going to look at that later. Okay? And the details are so messy that I'm not going to give you all the details. But you'll get the basic idea. Okay? I actually went to the path. I designed a shared centralized window assignment for you also, which I just removed. Okay? Here's the question I want to ask you. Can multiple users generate a stream that is not created by one user? We are collecting input from multiple users and giving it to the application, right? If it's replicated, we're collecting input from multiple users and giving the collection to all the replicas. Okay, in the single user case, there is some not legal in the mind of the user, legal in the mind of the application. There are some legal streams that it accepts. Is it possible that when the application is replicated or centralized in a shared mode, the application gets a stream that was not generatable by a single user?
If two users are trying to use the mouse at the same time, we can see like two mouse press calls without a mouse release event. Mouse drag events in two different parts of the screen at the same time.
Okay, you can see two mouse. An application expects a mouse up, a mouse down to be followed by a mouse up at some point, and before it's pressed again, it expects that. And what happened? I press the mouse, you press the mouse, and the application has not seen a mouse down or mouse up. Okay. So press left button. Okay. Mouse button, left button up or down actually goes to the application, and press left button, and you've got these two. And these systems used to fail a lot. And X Windows system, which is what I'm familiar with, which has been the inspiration behind many Windows systems, would break, I believe, if it got these invalid sequences. Okay, and when I gave you guys the assignment, I was really worried that when we inject remote events with the local events, who knows what's going to happen to the application? And I still don't know what's going to happen on your Macs. And so, if you're not going to build the, you might as well download the virtual machine for the PC just to make it work. But hopefully it'll work. Okay. And the Windows system is more resilient to these things, I've noticed. So multiple users can indeed generate and can break assertions of collaboration unaware code. Okay, and that used to happen. And the solution is, there's no other solution to this. You have to have explicit floor control. Floor control is just a lock that is shared by all the users. So just as when somebody's in a room, one person has a floor, you have one person having the complete lock. Okay, you can't have locks. You might be able to have fine-grained locks also, but most Windows systems came with floor control. Okay, that you would pass the floor to another user. And then I saw in Vista. Vista is this this operating system that was probably the worst one that Microsoft ever came up with, because it tried to do too much. I still have a Vista machine running, an old machine running. But it had this shared Windows system without any floor control. And I tried to break it, and it wouldn't break. So, I think Windows is resilient to these things to some degree, and I don't know how they managed it, but that was the first one I saw that didn't have a floor control. So one user interacts at a time and explicitly gives floor to another. Okay, and the nice thing about floor control is that it's automatable. You can build your floor control machinery that works for shared model systems, shared Windows systems, anything. It's just orthogonal. Okay, that's what you will do in your next assignment. And this problem occurs in both centralized and replicated shared Windows systems. So, plus other problems, you have invalid Windows sequences possible because intra-sequence constraints in Windows system get violated. Okay, now we're going to have problems because we're going to cheat. Right? We are cheating by not doing pure WYSIWIS. Pure WYSIWIS means everybody sees the same thing. Okay, we're going to relax WYSIWIS. Okay, but yet we have only one master computer. So in centralized system, that's a problem. They almost don't go together with each other. Okay, we want to do relaxed WYSIWIS and yet have only one application processing all events. Maybe that's not so contradictory, because after all, the window structure is created at each end, and if I move the window here, my movements don't have to be sent to you, so the windows are replicated, so I can move them. But we'll see a few problems. Okay, so let's go and see first what it means to do pure WYSIWIS. Okay, pure WYSIWIS means that at the slave computer, if the user moves, that move event is sent to the master, and that move doesn't have to go to the application. The application doesn't do the moving. It just goes and gives it to the Windows system, and the Windows system goes and moves it. Okay, so here's some event processing that is short-circuiting the application and going to the Windows system. And so now all the windows are move coupled. Okay, so this is what is WYSIWIS. Now let's go to non-WYSIWIS. Okay, so this is going also to the other slaves. So they're all in sync, and window moves and all. Okay. And this is a system that's a real system. Okay, XTV. This was a system built at UNC by Hussein Wahab, who was visiting here, and he was visiting Kevin Jaffe. So Kevin and Hussein and I don't know who else were involved in this project. And you see now, this is built XTV. X, I was talking about. How many of you had heard of X before this class? How many of you use Linux machines?
You mean X, like X11, X1?
Yeah. Yeah, your Linux machines run X. Okay, so this is not a, so this was before Windows 95. Okay, when Apple had some Windows stolen from Xerox, and Microsoft had no Windows, and the Unix guys were making doing all the research. And the Windows concept came from Xerox, and X made Windows remote. That was just beautiful. That you could, on your computer, access the windows of an application on another computer. Okay, you could do remote access. I mean, that was just great. I would go to universities, give a colloquium, and demo my application running at Purdue remotely. Okay, and so on X, people made Shared X was one product, and XTV was another product. Okay, research product. And you see here that my windows are not window positions are not coupled. My calculators are at different positions on the screen. This window is a different position. And you can see that certain window minimization also is not coupled. This window is maximized and it's minimized. Okay? So this is relaxed system. And here's a problem that the guys who did XTV found. Can you see the problem here? The pop-up menu is showing at different places on the two machines. If you did the obvious thing. So pop-up menu. Can you imagine why this is happening? I mean, all these things. If this is a sub window, it's positioned right. This is a sub window, it's still positioned right. And X was one of the big things about X. It was it made Windows very lightweight. So you could have sub windows, like and people. Every calculator button was a sub window. Okay, and it was lightweight. It was fast. It was great. It's still great. Why is this particular sub window positioned correctly, but this window is not? Yeah, Nick?
Okay. The menus were created at the same point in the screen.
Same point on the screen. So they were created the same relative point on the screen. These are sub-windows of this window. A pop-up menu is not a sub-window. Okay? You expect it to happen at this cursor position, but that window is a separate window that's not related with that's not a child of the frame. Okay, and so that's what happened. And the absolute position is the same. You see here, but the relative position is not because of this. So a pull-down menu, a pop-up menu, all of these have the same property. Have this property. Okay, menu bar. If you look at the Java hierarchy, the menu hierarchy is just this whole different hierarchy. Okay, it's not the menu. Okay. So that's the problem. I should say pop up and pull down menus. This is a pull down menu, right? I clicked on a button. I guess that's yeah. So inner windows drawn relative to containing window, but that is not. And so what XTV had to do was to put enough context on the slave and the master so that it'll occur the right position. Okay, it had to know that this window was created in response to a click here. So now my slave system, my distributor is no longer just a little distributor. It's got intelligence about these windows that are getting pushed, these pop-up menus and pull-down menus. Okay? Understands underlying window system. And that's not uncommon in policies. Okay? I'm going to tell you a lot of stuff that has to go in these things. And when we guys were doing research and building these things, just like your assignment, we created these systems. And then I heard about people charging you by the minute for shared screen. WebEx was this new company that came up and said, you want a meeting? Pay us by the minute. And we'll go and do shared window systems for you. And I said, I have a little grad student do this. Why do you want to go and pay by the minute? Because we didn't solve all these real problems. Okay? And solving all these real problems is painful. Okay? And you guys get the basic concepts in your assignment, but there are all these issues. Okay? And the point is that I said, just got to build a distributor and a multicaster. Okay? No, you've got to build a lot of intelligence about the underlying system. Okay? In fact, XTV was, I said, Hussein was the one who was the pioneer behind it. And he laughed that he would use XTV to give remote lectures. And he always knew, he always would prepare for 40 minutes rather than 1 hour lecture, because 20 minutes would be spent in making it recovering from crashes. Okay? And he just, one day didn't crash and he didn't have enough material, I think. So these guys who are charging you money now, they're really giving you value for it. Okay, here's a little issue that I haven't addressed properly. So anyway, we addressed it to some degree. So one of the questions is, should window state be coupled? And coupled window state means window wars. We saw that earlier. Uncoupled, we don't have referential transparency. We can't go and say that upper left window. Okay. And in centralized systems, we see that there's a problem that we have to make our proxies, not just proxies, but basically implement some window system intelligence in them. Okay. Can we somehow get the best of both worlds from a design point of view? We want referential transparency. We don't want all these issues here. And yet we don't want window wars. So the problem with window wars was that you moved your window on top of my mail window. Right? And I'm going to move the window away because I want to see my mail window. Can I have a referential transparency? Can I have all the good things about coupled windows and yet be able to see my mail window? How many of you have done a shared desktop? Not a remote desktop, but a shared desktop. Google Hangout. You have? So have you been sharing somebody else's desktop or making other people share your desktop? Okay, when you were sharing somebody else's desktop, and was your mail window obscured by that shared desktop? Was it an issue that the other person's movements caused your windows to get obscured and you couldn't recover from that problem without moving the window back? What did you see on your screen?
When you do the shared desktop, obviously you're going to see yours, and then it goes to yours. You're going to see how to close on that window.
So what happens is that the masters, you build we'll just see it here. Create a virtual desktop on a slave computer for physical desktop of the master computer. So you're not going to share individual windows and put them arbitrary places. You're going to take all the windows of the master computer, put them in another top-level window, which can be moved around. Okay? This is what this is saying. So this is live meeting. I used it. I have a window on my screen. I'm a slave. This is a window on my screen, right? And there are other windows that can be Gmail windows, which are my private windows. And all of the master's windows get put into my virtual desktop. Okay, this is what you see with the shared desktop also, right? When you share a desktop remotely, in that case, you take all the windows of the remote computer and put them on your virtual desktop. Here you take all the shareable windows of the master computer, put them in a bigger rectangle, and if you think that the rectangle, and you can position the rectangle anywhere, so that your private windows don't get obscured. Still, if you want to go and have, so this is a little confusing maybe because this sub window is showing you my virtual desktop slide. Sometimes these recursive PowerPoints cause problems. But this is just my PowerPoint application getting shared, some other application getting shared, and this is the master window. And if the master goes and moves this window remotely, in the virtual desktop, the window will move remotely. But this window is just so I think this was actually a brilliant idea. Nobody ever talks about it, but this was, the problem that the Xerox guys faced with window wars has gone away, and yet you have referential transparency. Okay, so people just I forget where this was invented, but very quietly the people solved this problem. Okay, so private scrollable movable window representing master screen, and nested shared WYSIWIS master window in it. Okay, and pop-up menu is not a problem, but now your slave system is creating a whole desktop. It's far more than a proxy. Okay, this is where your money is going when you go and use WebEx. Okay? Because it has to go and do window management, it has to draw things in there, and so this was far beyond what XTV and what we guys in research did years and years ago. Okay. Question? So, okay, we're going to look at other problems next time. Okay, so I'll just stop at this point. Okay, so what you guys are implementing, and what we saw, a few slides ago, a few classes ago, is a replicated architecture where when a user inputs an event, that event is sent across to all the replicas, and every computer has a replica. Okay, and this is what nobody does. This is what you guys are doing, and we'll see why nobody does this. And we'll see why you guys are doing this. Okay, it has to do with implementation and generality. Okay, and the dual of this architecture. So in this architecture, input is being distributed and broadcast. Okay, so there's a broadcast notion here. Okay, and you're basically broadcasting the input to all the other replicas. Okay, case, what you have is an asymmetric situation. Asymmetric situations are harder to deal with in implementation, by definition almost. And you can see that why things are more complicated. So there's only one application running. It runs on only one computer. So input has to be distributed from all sides to that. It's being collected. It's not being broadcast, but it has to be distributed. Okay? And then out comes output, and that output is broadcast. So in one case, input is broadcast, and in the other case, output is broadcast. In both cases, we have to have proxies that translate window IDs. Okay, so that's something that you're doing that has to be done. Okay, and input has to be intercepted and distributed, and output has to be intercepted and broadcast. Okay, so there's more stuff going on here, and that is the reason why you guys aren't doing the centralized implementation. Okay, so before we went into these implementation details, we wanted to see just what the pros and cons are of replicated and centralized. Okay, and we saw that, look, by definition, centralization means bottleneck. It means delay. Okay, whether you're doing model sharing or window sharing, there is some part that's a bottleneck. That means some kinds of things have to go remotely. Okay, and so the problem of centralized model systems get aggravated for readable state. Okay, so if I'm just scrolling the window in your first assignment, no communication had to go elsewhere. No, the events didn't have to go anywhere else. Okay, readable state was fast, and if you did centralized model sharing, like in Google Docs, you go and scroll in your browser, it just scrolls privately. No events have to go to Google. It's only when you go and change the data that stuff has to go to Google. Okay, so and Google's Docs is not exactly centralized. We'll see when we look at operation transformation that it's a hybrid kind of architecture. Okay, but when you do remote desktop, Okay, so when you do remote desktop, you face the kind of problems we face in shared window systems, where everything has to go and come back. Okay, redrawing of the window requires a round trip. Okay, and so the centralized problems got worsened. The replicated problems also got worsened because the whole goal is we'll take existing applications and we'll share them. Existing applications may have side effects, may go and write to a file, may compute random numbers or be non-deterministic. So in centralized models, in replicated model systems, you're allowed to change the models. They're not trying to take existing compiled applications. So it's allowed to do that. Though of course, it's nice if you don't. So some of the problems that can be solved in replicated model systems don't get solved in replicated window systems. And that is the reason why commercial systems don't tend to implement this stuff. Okay? Plus, there are other problems that we did not have in new kinds of problems. Some problems got aggravated, plus you have new problems, and in both replicated and centralized systems, you can have invalid window sequences. Okay? Now, whether those invalid window sequences cause problems in the application or not depends on the window system. I told you in X that they cause problems. I've seen in Vista implementations where things did not cause problems, okay, without any locking. Then we saw also that in centralized window systems, when you have relaxed WYSIWIS, which means that my window does not have to be positioned exactly where your window is positioned. Okay? My window can be iconified, whereas your window does not have to be iconified. We ran into further problems of pop-up menus. Okay? That the pop-up menu is always shown relative to the coordinates of a particular window, and its coordinates are computed by the application process, and it's assuming its window's coordinates to compute the pop-up window coordinates, and so the pop-up window might appear somewhere else otherwise. Okay? So you had to go and make in your proxies were not just simple forwarders and distributors and broadcasters. They had to get knowledge of the underlying window system. That's what typically happened. That if you're building a shared window system for X, your proxy knows a lot about X. So and then if you're building one for another window system, it knows a lot about that window system, and that's why I've seen papers, different papers for different window systems, even though you might say there should be just one paper. Okay, and we're going to look at this obscured master windows soon. Now, when you do relaxed WYSIWIS, there's two ways to do it. Okay. One is you have exactly the user interface that you have today in your assignment. If you were to run your assignment on two different computers, what would happen? That the shared windows and the private windows would all be mixed together as one set of windows managed by the window manager. It's not as if the shared window is somewhat special than a non-shared window. Okay, they're just all mixed together. And that's what's happening here. This is XTV, and I guess I really ran, this is me running XTV. So actually I ran XTV on and which version of Windows is this? 97 perhaps? Oh, no, this may be 7? Okay, so I actually ran it. So XTV was running at that point. I don't even know how to get hold of an implementation right now. But I ran it. And you see that this calculator is positioned, so one of them is the master, the other are the slaves. And you can't tell right now who's the master, who's the slave. But let's say this is the master, then the slave has got the window mixed with his other windows somewhere, that the slave chose to put it. And similarly, this window is a different position. And you can minimize the windows separately, independently. So this is what happened in XTV. Okay? And the windows were all mixed together. And what's the alternative to the windows being mixed together? We saw that last time quickly before I stopped.
The windows all being in specific positions according to the master.
Okay, so that's relaxed WYSIWIS versus WYSIWIS. In both cases, the windows are mixed together. In one case, the coordinates are following the master. Okay, which we saw was a problem. Okay. When you do a
virtual desktop.
A virtual desktop. When you guys do a remote desktop to another computer, you can still access your windows, right? And what you do is you take all the windows get put into all the shared in remote desktop, all the windows get put into a virtual desktop, and that desktop is a window in your system. So to your system, you just create, to the window manager on your system, you just create another window. That windows have sub-rectangles which correspond to the windows in the master. Now you're doing far more work. Okay? And I don't know who invented the notion of desktop. We academics did not, from what I know. Okay? And then I think what really happened was So the first time I saw it was when I ran this product in Microsoft Live Meeting, and it's very interesting. So I talked about the X window system which Linux uses, and the X window system has this very nice property that the window system and the application are two different processes. That was just such a wonderful invention in the late 80s. And then came Windows 95. And we couldn't understand why Microsoft did not see the obvious advancement that people had made and went back to the pre-X days where the window system and the application were all part of one process. Okay, they couldn't be distributed. And we wondered how you could do remote interaction. And historically what happened was Microsoft acquired NetMeeting. NetMeeting allowed multiple, so NetMeeting might have done this actually. NetMeeting allowed multiple users to share an application. And then they said, they acquired NetMeeting, and I don't know whether the people from NetMeeting joined Microsoft or not, and they just are having a terrible time maintaining that software and all the security issues that arise. So they took direct NetMeeting, took out the multi-user facility, and just made that into a remote desktop facility. So it's very interesting that their remote desktop came from multiple users, where they just said it's either one user, this remote user, or the local user, and the desktop got mirrored here, and they made that a very nice product, the remote desktop, RDP. And so then when I was at Microsoft, they were taking that thing and making it back collaborative. So they started with something collaborative, made it remote, but that was their way to handle X-like situation. That you do have on your computer, on the one computer, the application running with its windows, and another place you just go and replicate the windows, and on the original computer you just blank them out so that you can't interact. But it's really two windows. There's really two windows created, whereas in X, your program runs on a supercomputer. The supercomputer doesn't even have a window system, doesn't even have a screen. There's no window created there. And you just create a window on the remote base. So that's a nicer architecture, but they were able to get the X-like facility through this virtual desktop, and then they took the desktop and made it, replicated it. Okay? That's what they did in Vista, and for free. NetMeeting was free, Vista was free, the shared was free. And then they just said, why should we give things for free? I mean, this is the problem they always have. Should they have Outlook Express and Outlook? If the Outlook Express is very good, then who's going to buy Outlook? And if if NetMeeting is so good, who's going to pay for Live Meeting? So they acquired Live Meeting, where they're making money out of that. So I think basically they started hiding NetMeeting so that people wouldn't find it, and then they just, I think, have got rid of it. Okay, so I could find it till Windows 97, I think, or even XP. I could find it, but I don't think I can find that in Windows 7. So they've got it on anyway. So that's the history, and that's what you're seeing now here, that the desktop is replicated. So this is my real desktop. Real desktop has got my PowerPoint slide, in which I'm making my slides on virtual desktop. Okay, these recursive things sometimes are very confusing. And this is another computer where this whole screen is now a smaller window in here, which I can scroll. Okay, and multiple people can be sharing this at any time. Okay, this is Live Meeting, I believe I'm running. Okay, I might be running NetMeeting for all I know. So you guys get the idea? And now we don't have to worry about window walls, because if I move this window somewhere here within this particular virtual desktop, the sub-rectangle will also move, so we can talk about the rightmost window or the leftmost window and so forth. Okay? Now, do you guys see a problem? What's the problem? This is black and this has got... So what's happening? Sorry? Start menu is a window, actually.
So the problem is the window that you want to share is not the topmost window.
Okay, so the window that I'm sharing is being obscured by some other window. So why do I see black here?
Because start menu is a window that is not shared.
It's not shared. So I should see black here, right? Or something else? Okay, so that's a very interesting thing. That my master, yeah, Nick?
That part of the window isn't being drawn on the master either.
Okay, so there's a lot of stuff going on here. There is the end user, what the user should see, and there's the implementation criteria.
Isn't
Okay?
being updated either. Like the image buffer we were talking about, like in Java, is the responsibility of the application to draw its own components.
Right. So it's the responsibility of the application to draw its components, and the application may be smart enough and not draw outside, not draw in portions that it knows are not visible. Okay? And if it was doing that, then maybe what should this show? Black or the old contents or what?
The old contents would probably be more logical because the user probably can't change them if they can't see them.
Yeah.
So your odds of you missing something are so low that it's probably a better experience not to put a big black.
Or just spinning
But-
and flashing question marks.
Yeah, maybe just.
But
have the
it
whole
can
thing
still be changed. Even the user can see it. Since the local process may change it
So
over.
assume that it's not for 20 minutes.
Okay.
So
Firstly, there's no local process.
clear.
This is not replicated system. This will not be a problem in replicated systems. In replicated systems, my replica is drawing on my exposed area, your replica is drawing on your exposed areas. Everything is nice and clean. Okay? Here, there's a master, and the master, could be the programmer could be a lazy programmer, it could be a very conscientious programmer. If the programmer is conscientious, the programmer would find out what rectangles are being shown and draw only there. Okay? In which case, this would be old contents. If the programmer is lazy, the programmer could be drawing in the whole window. In which case, I could see the current contents right here. And you couldn't. The master couldn't, and I could. Should that be allowed from a usability issue?
But the master's performance may be not that good since he needed to draw some windows is not visible in order to share this.
Oh, so you're saying that's an interesting point. That this stuff the master's not seeing, and to send this information to the other end, you need some bandwidth. Why are you wasting that bandwidth? So then you're kind of implying that the other guys should not be able to see the stuff that the master is not seeing. So that's a fundamental question. Should I, in a remote place, be able to see something that the master can't see?
Depends on a lot about so I use Google Hangouts a lot for sharing particular applications.
Yeah.
And its behavior is that if it's behind other windows, it's still sending whatever is on those windows. So if I'm looking at something else, it still sends the stuff in the background.
And you know that from what?
From experience, I've been having a terminal shared, and there was some long-running process, and the remote person that I was conferencing with told me that a process was done, and I hadn't flipped back.
So they made that decision. Live meeting guys, I believe, or whatever tool I'm using here, decided that they wanted privacy. That what if something is here that the master doesn't want you to see? And they can very quickly go and obscure it, and here they can't.
Yeah, I guess their approach is just if you don't want the user to see it, don't share that window.
Right. If you don't want the user to see, don't share it. But these plans, these decisions sometimes made early can be wrong.
Right.
Okay, sharing is a very tricky issue. When we get into access control, you'll see that. So, but anyway, people don't talk about this, but this is a very interesting. This is an interesting issue. So let's see what all the possibilities are. So of course the problem here is that there's this window that obscures this window, and we see a black thing. And I'm very curious what other people have, what decisions other systems have made. I would have made the decision that Google Hangouts made. Okay. So firstly, corresponding windows on so whether this is a problem that occurs regardless of whether you're using virtual desktop or whether the windows are first-class windows in your system. Okay? The fact that there's only one master process drawing to the windows, and the fact that those windows may be exposed differently, whether they're part of a virtual desktop or they're independent windows, is not an issue. Okay? So let's just remember what happens. Whenever you resize or obscure a window, appropriate events go to the application saying, this is the part of your window that is exposed. And in Java, I believe there's only one rectangle that's sent, which is the biggest rectangle that's visible. And it's the application can be lazy or may not be lazy. Okay? And if the application is lazy and draws in the whole window, the window system just goes and clips the portions that are not visible. Okay? And if you're computing a lot, if you're doing some very heavy computations to create an image, then the application has wasted its work. Okay? And wasted time. So let's go and see all the cases that are possible. Okay? We know that windows may be exposed differently on different computers. So a resize or obscure event occurs on one computer, on the master, let's say. The rectangles are sent, the rectangles are received, and the window application is very diligent and draws only the exposed parts. Okay? So it draws the exposed parts in its local window system, and which those parts are then clipped, and it draws the exposed parts, it sends the same thing to other window systems, and they also draw the exposed parts. And then the question becomes, what should these systems do with the non-exposed parts? They can just let them remain as old content, or they can go and hide them and blacken them. Okay? That depends on the user interface. So each computer shows only regions exposed in master, and slave can show either old contents or black holes. Okay? The slave has those contents in its screen buffer. Okay? It has to do more work to fill it with black pixels than to not do anything. Okay? So this is an implementation issue, and personally I would go and say, let's just see the old contents. You know, they were there before, I could see them, but you might argue that the master just saw that some private email, some notification came into that window, and they want to quickly hide it, and you should not be able to see it. Okay? And just to show you why this thing is dynamic, there's been this big case of some financial company whose name I forget. They accidentally send emails to the wrong set of people. Okay? Gmail completed the email as something versus something.com as something else, and the mail had gone. They contacted Google and said, please don't let the users see in their inboxes those messages. Okay? Because in Gmail, you don't cache the data typically. So you might have seen the email once, but the next time you won't be able to see it because Google just removed that stuff. So this is akin to that. Nick?
I was going to say, isn't there a problem if we're showing the old contents, that the old contents could become stale in a way that's misleading, especially if one of the users doesn't know that region is stale?
That's a good point. So if the old contents are shown, they can get stale. So maybe rather than making them black, they can just go and put a rectangle around it. But they must have thought about this stuff. The fact that I saw black holes there, and the fact that people are typically lazy about programming, tells me that they did extra work. I don't believe that application programs go and draw in exposed areas. I think they draw the whole window. So the fact that I saw this means that they must have thought about it, and they just decided that they were not going to. And there must have been cases. Customers must have complained. Did you ever feel uneasy that those people could see things that you couldn't?
No, I mean, I think you're all, like, I don't know, whenever I screen share, I'm always paranoid, so I always only share, like, one window that I know is going to be clean.
Okay.
If it's a browser, I'm going to be running in, like, anonymous mode or whatever.
Okay. So this allows you to be less paranoid and share more.
Really, there's still a chance of a mistake, even if it's framed. So
But there's an audio conversation going on. There's a lot of stuff going on to avoid these problems.
Yeah.
But yeah, I mean, this is all these technical issues arise when you're designing things. Okay, and exposed events are not sent from slaves. That's an important thing. That if you go and, if you go and cover the window, we won't send the exposed events to the master because otherwise it gets too confusing. There's no reference point, right? So just as when you move the window, you don't send those events. In this case, the exposed events are sent from the master to the slave, but not from slave to master. Okay. It's interesting. I actually made this presentation to the live meeting guys, and they had acquired a company that did the window system, shared window system. So they didn't know about these issues, even though they were the ones from Xerox who were selling the stuff to Microsoft. So this was new to them also. Okay, now what happens when the application draws a complete window? You resize obscure, you send all these rectangles to the application. It says, no thanks, I don't need the rectangles, I'll just draw the whole window. You draw the window here, clip, draw, and slave shows obscured contents in master. Slave shows contents not seen in master. And how to overcome problem? So sorry, I said earlier that the exposed events are sent from the master to the slave. No, exposed events are not sent at all. The drawings themselves only drew on the exposed areas, and that's how you got information about the exposed. Now you're getting no information about the exposed areas, because the application is drawing in the whole window, and if you really want to go have the slave hide the window, the slave you have to do it. And what you have to do is send the exposed rectangles not only to the window application, but also to the remote machines, saying, no matter what the application says, this is what you should show. Okay? And then what will happen is you said draw, and it goes and says, okay, I take your draw, I clip it to the rectangles I know about, and then my window system will further clip it. Okay? So there's again more work being done for this privacy thing, and either the Google Hangout guys were just lazy, okay, and you said the performance is not that very good, or they thought further than whoever did the work for live meeting. Okay, so, okay, questions? So again, a summary here that when you do window-based coupling, window sizes and window contents must be coupled, otherwise things won't just work. In the window position, stacking order, which windows on top, which windows below, exposed regions, they can be, they may or may not involve remote communication. And the optional part can be done with or without virtual desktop. And with the virtual desktop, there's no danger in sharing the stacking order and positions. So they do, okay? And the virtual desktop, I think you as a slave, you can't even change the stacking order. So maybe this is a little misleading what I just said here. But in both cases, exposed events are an issue that proxies must address. Okay? So that's why I spent all this time talking about exposed events. Okay? Okay, here are some more problems that arise when you build a centralized window system. Okay? And this is a problem that certainly arose in X case. It may or may not arise in the modern window systems. So let's talk about input and output. Okay, so you press A, that's input. You move a window, that's also a form of input. Okay, the application can react to a window movement. You resize a window, obscure it, that's also some user action. Okay, you can think of that also as being user input. Okay, and you get all these events, and all of them involve transferring info to the application based on window actions. Okay, the application goes and draws something, moves a window. Now that's like an output. Okay, application took some action. The UI must react. Okay, that's output. Okay, you draw and expose windows. That's output. Okay, so that's clean. What about something that's neither here nor there? The application goes and says, list the fonts. It asks the window system, tell me what fonts you have so that I can draw using those fonts. One of the biggest issue I used to have when I would demo my application remotely with X was the computer on which I was demoing didn't have the fonts that the application required, and it would crash, okay? Because the application maybe wasn't doing list fonts right or whatever. Okay? So I've colored list fonts in green because that's something that came from the application. But is it input? Is it output? The request went. It's a procedure call. Okay. It's an output request call transferring info to application. Can you see this causing problems in a shared window system? Nick?
If we forward this to each user, like we've been doing for other outputs, then either we only get a response from one user, which isn't accurate for the other users, or we get multiple responses, and the collaboration unaware application won't know what to do with that.
Yeah. So what do? Do we send the request to one computer? If we send it to one computer, which computer? Do we send it to all computers? And list fonts is easy. We're expecting a list, so we can go and take the answers from everybody and put them into one list. And the collaboration-aware application is fine with that. But what if it is query pointer? Tell me the position of the current mouse, the pointer. Okay, I query that rather than getting events. Now it's expecting one position, and what does it mean to get 10 positions from 10 users? What do I give? The average? So, headaches for the shared window system, guys. Okay. And so you can unicast to master, okay, which is sort of the obvious thing to do. The master says, okay, I've got font number 5911, and you send that to the window application, and maybe that works fine. Okay. Maybe it doesn't because the window systems on the other computers are asked to draw something with a font they don't have, and they just crash. Okay. You can go and broadcast the call, and with list fonts that works just fine. Okay, you get results from all three computers, and now what do? You take, and if you list fonts case, you'll go and take the intersection, ideally. Okay, and say, okay, you've got these two fonts, and use them so that it's the lowest common denominator. Okay, so a call with return values may be broadcast to all window systems, and the master proxy can combine replies. So again, we're seeing that we're not just distributors, just all this work being going on. And one of the things that, the lessons we come up with is that maybe the window system should be designed differently because to allow them to be shared. And this is what I keep telling you that I get frustrated because Java window system came after all this research happened, and they didn't care about collaboration. So that's why I can't give you a project on centralized window systems. Okay? Even though, as I will talk about later, it is possible to design Java in a way that allows shared window systems to be created. Okay? It's just that it's not part of the standard API. And you can also go and say, hey, I won't broadcast to the master. I'll just pick some arbitrary slave. So I go and send it to this slave, and I get the result back. Now, it doesn't make much sense, but theoretically, you could pick just any one of those computers to get the output back. Would it make sense to go and choose a specific slave and say, no, I won't choose the master. I won't choose to broadcast, but I'll use this particular slave because that's what makes sense. And what would the criteria be? Think of your next assignment. Anybody remember what the next assignment is going to be? Jitter, no. We voted to get jitter out. Locking. Okay, does that now make sense? Can you pick some slave who? Who?
It's like a leader's action. It's like a leader's action.
Leaders, who's the leader? Who's got the lock? Because that's the one who's entering data. So if I go, and this one has the floor. Having the lock means having the floor, because in Windows systems you get the whole lock. And the implementation you will do, I thought about giving you fine-grained locks, but just do overall locks. Okay. So you go and if you're going to say query pointer, tell me where your mouse pointer is, then you might want to go and send the request to the one who's active, who's moving the mouse pointer, and get their position. Okay. And so you get the data like this back. Okay, but so that the application can draw at that pointer position. And so a call with return value may need to be unicast to Windows systems with the floor. And this is, again, you should not be polling for the event. You should be getting event. You should be getting the event. Okay, but this was an X call. Okay, you could do that. And there were reasons. You could get the event also, you could query also. Okay, and I used to actually teach X a lot, but I've forgotten details. But there was reasons to do this. And you could grab the pointer. There was all this complicated X stuff. It was so complicated that most companies didn't know X. And I used to go to companies and have these consulting arrangements where I would teach them X. And it was a very complicated system. And so you can just argue. So some Windows systems are more conducive to sharing than others. If you don't have output calls, then you're easier to share than if you have output calls. Okay? Output calls that return values. Okay. So this sums up everything. In centralized systems with query calls, the target of these calls is an issue. Okay, that's a basic point, and it can be resolved in multiple ways. Okay, so I've given you the theory. I still haven't told you how to go and implement centralized Windows systems, but let me back off and let's talk about what the world has done. Okay, and let me give you a little bit of history because it's kind of personal to me. So there's a guy called Keith Lance. He graduated from Rochester, and he did a thesis very much like X, where the application was on one computer and the user interface was another computer. And he did it much before X. Okay, his thesis was 1982. And X said that the user interface that is remote is the Windows system. It's very low level. It's getting mouse events and so forth. And in those days, the network was an issue. This is before Netflix was a valid application on the network. So he said, let's go into high-level graphics at the remote computer. Okay, that you go and send high-level requests, and the remote computer. And his example was, you've got a supercomputer, you've got a user, and we've got limited bandwidth. So we'll go and do high-level graphics. Okay, and he had a very nice transactions paper on this. And then he went to Stanford, and he said, oh, you can do, why not do multiple graphics at one time? So he thought of shared Windows, shared applications, and he built a system called vConf. V was a system that did this high-level graphics, and in the early 90s, I was thinking of the same kind of problem. And one of my students was a guy called Dinesh Manocha, whose dad had taught me mathematics in India, and he joined Purdue, where I was teaching as a graduate student for 1 year. And Keith Lance left Stanford and went to a company called Olivetti, and Olivetti hired Dinesh as an intern. And he got to know all about the work being done there, and he said, hey, you're thinking about these things, come meet Keith Lance. And so I met Keith Lance, and I got these many papers, which are sort of seminal papers in this area. And so he was doing this work. There was a bunch of guys at Bell Labs doing this work too, and then there were these guys at UNC doing this work. And when I was leaving UNC, I was choosing between actually joining this group or joining this group. Okay, I ended up coming here, which is just as well because Bell Labs is still doing well. Okay, but this tells you what architectures they used. Okay, so the XTV, they use centralized. Okay, Keith Lance tried both replicated and centralized, and he wrote the seminal paper on Lance and Lauer's. I still have printouts of those papers lying somewhere that I got in my trip to Dinesh. because these are old papers. I don't know if they're on the web right now or not. But if you ever want to read these stuffs, I can probably dig out the printout somewhere, okay, in my messy office. And the Bell Labs guys just couldn't make up their mind. Just as I told you, the Xerox guys couldn't make up their mind whether they should go to WYSIWIS or non-WYSIWIS. They just kept. The Bell Labs guys tried the centralized architecture. It was very inefficient. They went to replicate it. It kept breaking. They went back to centralized, very slow. They went back to replicate it to see whether they could fix it. So this has been a real issue. Okay, and so what did the industry guys do? They all went to so research systems tried both architectures, and these are some of the industry guys, and they all went to centralized. Okay, and I'll talk about how they went to centralized also. It's not the most elegant way or the efficient way, or maybe it is. Okay, it's very different from what the research guys do. Okay, so let's go and talk about what problems arise in implementation. Okay, and why the industry guys implemented very differently from what and the reasons are partly what I've already mentioned, that centralized systems have all these issues, and we'll see what they did. But before we see what others did, let's go and see how could we have done centralized shared window systems using AWT. Okay, so why is centralized harder based on what you know about Java? In replicated architecture, must intercept and inject input. Okay, and already we are seeing that injecting input can cause problems, maybe on the Mac because the window doesn't have the focus. Okay, you must intercept input and output and inject both. You have to take slave's input, inject it into the master. Okay, which we already know how to do, at least on PCs. Okay, and we must take the output of the master, inject it on all the slaves. Okay, so two kinds of problems. Okay, now with input, there is an event queue. And by the way, your demo, if you work on multiple computers, it might work, because you can go and select that. I'm curious, because you can go and make that window the focus window, and maybe it'll work there. It'll be very curious if that's.
There are only another one window on the top, so maybe there are only one Windows manager, so maybe.
Yeah, you're demoing it on one particular screen, and you can't have both this window and that window be the focus window at the same time. But maybe it'll work on multiple computers, which is what it's supposed to work on, right? I have visions of next time I teach this course, making it very different. We were talking that maybe if the videos are good enough to listen to later, let's just have people listen to the videos, and we'll just do interesting assignments in class. And coming up with these interesting assignments would be a challenge. But at least when you have two people working together, then you can do real distributed stuff. You've got two computers there. So that's part of my vision. Okay.
So does that mean that the next class gets to listen to all the comments that we made in this class?
You guys are on camera. I still have. So the last time I taught, I made the YouTube videos out of 401. I taught I made YouTube videos. Some things I taught your 401 I did not teach to the last 401. Like there is one on shallow and deep copying, and so I took your slides and made them into YouTube videos, and you're pretty much the star in those videos. So
Maybe go watch them.
You and Marie, you're both the stars there. So, but that's what I'm thinking, and actually this is something I want to ask you guys at the end of the course. What do you think of that idea? That's the inverted classroom thing. And what I'm thinking is that in class, we'll take Google Hangouts, we'll take these practical technologies and do things with them. So it's not so you're basically getting the concepts in the homework, and you'll get the concepts a second time in a practical application. And you get to talk to each other and learn from each other, and the instructors here also. And so the coming to the class is a valuable experience, and maybe you get more from that than just okay. No,
actually, I think students will just skip the class and see.
You won't be able to skip the class. The class will begin with a little quiz on what you were supposed to have watched. Okay, And those quizzes will be yes and no. It will be multiple choice. Okay, so if you're a good guesser, you'll get through somewhat. And then you discuss in class which choices were correct and why they were correct. So you essentially get the class material in a different way, having thought about it. Okay, so I mean, you guys are not so much of an issue, though I was complaining last time that you were. But if you're 200 students, it's more easy to tune out. And the day that 401 classes really listen to me is the day after the midterm, when I go and say how their solutions could have been different. Because they were involved in something and I was critiquing them and giving them the right solution. So if I go and say, okay, this is the exam you just took, this is how you could have done it, they're paying more attention, you're learning the same things in a different way. So anyway, I want to get your input later. I'm excited because it's different. Okay, and you know, this is what I've been doing for decades. And this is much easier. Once I have my recording right, I just listen to the YouTube video over breakfast, and then I'm pretty much saying the same thing, right? I mean, I'm not doing it right now, but next time I could do it, right? And maybe that's valuable, because this is real. But isn't it like watching a live tennis match versus watching a video? Okay. Sorry, I lost my train of thought here. So, okay, so what happens here is that all the input goes through a particular event queue. And all input is defined by one data structure. That makes it very convenient to replicate things. Okay? And it's, like I said, it's all defined by one object funneled through a single thing. Now with output, how's output being done? Okay, this is a window application. It has a reference to a frame. Frame has a reference to graphics. And what happens? You can do set size. Okay, then the set size call has to be intercepted and sent to all the other computers. Okay, it's being done on the frame object. If frame is what it's doing it on, is the particular component we are wondering about. That we're trying to, that the call was made on. If it was on some other component, we'd have to go and send the set size for that component. Then the window application can call repaint. Repaint will call paint. Paint will go and call draw. And you have to take the draw call, draw line, draw whatever, and send it out to the other side. So these calls are being made on different instances of different objects, and there is no data structure describing all of these things. And there is nothing through which, there's no object through which all these output calls are being funneled. Okay? And if I was going to make an assignment for you and was willing to go and change things so that you can't, now you can't take just frame, you'll have to take my frame. Okay? Because frame doesn't cooperate with me. How would I change frame or graphics to allow centralized sharing to occur? I'm not going to re-implement frame. So I'm going to use the current frame. I'm not going to re-implement graphics. I'm going to use the current graphics to some degree. And let's say I'm going to inherit from them. What will my inherited frames and inherited graphics do? Every time I get a set size call in frame, what will I do? Send to?
Centralized manager.
Send to some centralized manager?
Yeah.
Okay, and what would I send? I would send some kind of data structure?
Kind of like a tuple as this comment says live and the parameters are the new slide.
So I can define a proxy that forwards the call, but I need to go and I need to solve the two problems I just said occurred. I need to go and forward that call. I need to go and convert the call into some universal data structure that describes calls with arguments. Exactly what you're saying, right? Similarly, I do the same thing with graphics. When a draw call arrives, I go and forward the call with its arguments to some guy. So you can do it. Yeah.
Hey, how would we control which graphics instance is provided to the paint method?
So how would you convert? How would you do that?
Because currently we're provided with a graphics instance
Yes.
by Java.
So how would you go and change the graphics, right? You put that graphics object, embed that in another object. So my paint method in frame will ultimately the frame goes and dispatches the method. So I'll have a paint listener. Okay. So we'll use the delegation model, and I will go and give it an encapsulated graphics object. Okay. So my clients will not be subclassing of the frame. They'll be defining paint listeners, just as you have to define paint listeners for your telepointer assignment. And I just give it a listenable graphics. Okay, so this is what I did. So calls to both frame and graphics must be intercepted. Java is not designed to allow interception. Calls are made by making different invocations, not by passing a unified data structure. So how to change them? So in your library, there is an object called a delegate frame. I did this only for frame objects. I could have done it for all kinds of components and containers. And now my window application is structured differently. It goes and adds itself as a paint listener to the delegate frame, and is given as an argument an object of type listenable graphics. Okay, listenable graphics has a draw method, just like all the other ones that the graphics does, and it just forwards the draw method to the graphics object, and it also forwards the method to anybody listening to it. Okay, and basically the listener is some master, and we come here. So here's my output queue. Just as we have an input queue, I'm going to have an output queue, and you guys just have to deal with an output queue, and you can just add yourself as an output listener. So the application firstly has to change. It has to go and paint to listenable graphics rather than paint to graphics. Okay, it has to add itself as a listener to delegate frame rather than a subclass of delegate frame. And you will just go and say an output queue, add output listener this, just as you did that for the input queue. And whenever set size occurs, it will go and notify listeners and will give it a serializable frame request. Okay, just as you have serializable, just to make things easy for you. And similarly, when a draw operation occurs, it says notify listeners and it's a serializable graphics request. Okay, and anybody who's a listener will now get these serialized requests, and they can just form. Okay. So I went through this whole process. I did it, and the trouble is that the application has to change. It has to use delegate frame rather than frame. It can't subclass the paint method. It has to go and add itself as a listener. So it wouldn't be, I would have had to tell you in your first assignment, please use these components of mine, and then I have to document them and all that stuff. So I just said and anyway, it's not as satisfying. Shared window system is supposed to take existing applications and share them. So that's why I just abandoned this thing, even though I first did this. I first did this because most systems do centralize shared windows, and I said this would be more realistic. But it's realistic in one dimension, not realistic in another dimension because you're not using AWT.
This you will do only in the centralized case, right?
Yeah. Replicated, you got what you got. Okay. Events are still going through input queue. So you add yourself as an input queue listener, as an output queue listener, and you do your centralized system. Okay, and then you can compare the performance of centralized and replicated. So, okay. So all frame calls and listenable graphics calls send to output queue, and output queue, like an extendable AWT queue, allows listeners. So that's the basic point. Okay, and just to show you that I actually went quite far and I really implemented things. So now you see that this is how my application is structured. It implements listenable painter rather than subclassing of an application, which is pretty much what I make you do with a telepointer. Okay, but telepointer is my abstraction. I'm not taking somebody else's abstraction, so I can do it as I want to. Okay, and your paint method is taking now the delegate frame and listenable graphics and then it's just doing what it would have done otherwise. And here's the interesting point. So we are logging the output calls, right? And sending them across. But those output calls have to be broken up into chunks by paint methods. Each time a paint method is called, it generates new events. And you want to display at the other end the last chunk and not the whole sequence. And you don't want to go and display, from one paint call, you don't want to mix those two guys. Okay? It's not as if we should do half of this and half of that. It should be a transaction. So that was another issue to worry about. So for each frame, need to track graphics requests issued in last paint call, and then bunch them into groups. Okay. So this is in X. There was no such thing as a paint method. So we just took the whole stream and sent it across. Here with the Java semantics, things are broken up into categories, and we know about this breaking up, so we can use that to do some kind of compression. Okay. So here's my serializable request. It has everything was done for frames only. You couldn't have subcomponents. And the name of the request, the arguments. Okay, we were talking about that. We just send the arguments. There's just object arguments. It could be anything. And here's my serializable graphics request. And for each request, I have to add a little constant. Okay, and I just have done these many. Draw a line, draw a rectangle, and then I have to also say whether this is a paint start or a paint end request. So there was another kind of request that you could have. So before the paint method was called, I would generate a paint start, and after the paint method, just before it ended, I would generate a paint end, so that the distributor could go and use that information to send the information across. Okay. And for frames, you have create frame and set size. It's the only operation that are allowed to be sent for set size, which made sense. Okay, so that's how it would have worked. Okay, we still haven't solved the mystery. How do current systems work if they don't provide something like this? If they don't provide such a queue, how is Google Hangouts working? How is live meeting working? What's really happening? And how is it working? I kind of got an answer from you last time.
I mean, it's I'm not exactly sure. It's just kind of sending video across because it's only like one way.
But the input is both ways, right? You can control from the other end.
Yeah.
You can't have multiple users sharing the application?
No, it's just screen sharing in the sense of broadcast of the screen to all the other users. So it's view only for everybody but the one person.
Really?
Yes.
But can you change the floor?
Yeah, I mean another person can jump to their screen.
Oh, but you can't share.
But you're not really truly sharing the same. So it's a hard kind of. It's not the same as this. Sort of
Oh, okay, that's interesting. I have a research undergrad looking into using Google Hangouts for doing. So I'm building for 401 a help environment where we can help students, and he just sent me mail saying Google Hangouts is probably not a good reason for various reasons. And here's another one, I guess. Oh, that's interesting. You know that you've tried it, and there's no control at all at the other end.
And not out of the box. There's like Hangout extensions and stuff
Okay.
that people can write. So maybe there's some sort of input over there. But since it works, like you can have one person on Mac, one person on Linux, one person on Windows, and they're all kind of sharing their screens and going back and forth. But
Okay.
yeah, it's not the same.
So we'll just say that input one can intercept and inject. All systems allow that. And input is key. It's very simple input. Output creates a lot of problems. Okay? And these calls like draw line, draw rectangle, they're just a pain. So what are we going to do? We're going to go to the lowest common denominator. We're going to take the images. Okay? How do we know the image has changed? We'll just poll. Okay? So we'll just keep looking at the image and say, has it changed? Has it changed? If it has changed, what is the diff? And send diffs across. That's how I believe all of these commercial systems are working today. Okay? All the stuff that we research guys had to deal with, query pointer, list fonts, none of that stuff is really being used. Okay? And that's exactly what all the academics said we shouldn't do, because bitmaps are expensive and networks were slow. Okay? But if you're sending Netflix, you can send these bitmaps also. Okay? So things have changed. And at some point, I will talk about how one can do things efficiently, what kind of coding you can use to reduce network bandwidth. So local infrastructure module can send screen diffs to other computers. So it's just sending these diffs. What's triggering it? Just polling. Okay? And in today's web world, where you poll the server to see whether something has changed, all the things that one taught in operating systems, never poll, that's being done today. It's not so much event-based sometimes, so maybe not such a bad idea. And intercepting output needed only in centralized architectures. And like I said, there's a lot of interesting techniques to go and make sure that it's efficient to send this stuff. Okay, I have, let me just finish this unit, and I'll just take maybe 2 minutes extra. Okay, so what did we do in your project? In your project, there's one VM, one process, and we put a proxy inside there. Inside somebody else's process, we injected code. Okay, so if you're talking about a compiled program, now they have to compile the program with your code. Okay, or at least run it with your code, link it with your code. Okay, that's not very realistic. You want to take existing applications into which you can't inject code that you go and then share. Okay, so the actual architecture. So in Java, okay, so there's 2 things. We assume that the Windows system and the application run in one address space. And in that same address space, we went and put our proxy. Okay? So this is the Java Windows system. Okay? In our thing, we put the library in a separate process. And now the question is it true that application and Windows system run in one process? Yes, on Windows it's true. Yes, on Macs it's true. But not in Linux. Okay? In Linux, they're different processes. So when you have this situation, and window app and system run in the same process, library proxy like this is possible, but it's not as practical. Okay? Because you've got to inject that proxy inside the address space. Okay? So what do people do? Fortunately, this is something I believe that they've designed the systems to do. Another process can intercept the window events of your process. Okay? It's possible in Windows and Mac and Android to go and intercept the window events of other applications, to build a proxy like this here. Okay, so now what you will do is you build your proxy in a separate process, and this process will listen to all the VMs around and not just the VM that you're sharing. Okay? And it's possible to do that at a very low level. The operating systems today allow that to happen. Okay? So that's what really happens. But what X did was this architecture, that your application and the Windows system were different processes. That's what happens in X11. Okay? And life is much easier. So to put a proxy here, what would you do? The question is, how are these 2 guys bound? Okay? This application, whenever you run an application, it looks at an environment variable. Okay, you guys know what environment variables? So when you do your main, the main has got args plus environments. So this particular program had an environment variable called host, xhost. And that variable pointed to this particular system. Okay? So the Windows system was a Windows server. Window app and system run in different processes. And what you did was you just said set environment host ID to this port. Set environment, and you gave a host ID and a port. Okay? And what do you do now? You put a little process there. You tell this application that the proxy is the Windows, is the X system. Okay? So you go and say set environment, host ID, port prime. Maybe even host ID prime you can do too. Okay? But you can just say localhost and port prime. So it thinks that is its X server. And to this particular process behaves like an X client for this guy. So you go and set the real host ID and port in the proxy. Okay? Which is what happens in web proxies, all these proxies today. You just put a process there that to the client appears to be the server, and to the real server appears to be a client. Okay? This was so clean, and that's why the term proxy makes sense. Okay? And that's basically it. There's a lot of text here. Okay? And it's mainly for your revision when you go and study for the exam. Okay? And we'll just end at this